correlation theory. The difference is what comes from the integrals. And it happens that in the integrals, you have a very long running of alpha.
Based on these works, in fact, continuation of this work here with we work Cesar Ayala, I, and Diego Teca. We will use Aleph data for semi-hadronic tau decay with the cutoff 2.8 GeV squared to eliminate the last two beams with large uncertainties. The weight functions in the sum rules will be Borel-Laplace. And as an additional filter, we will use finite energy sum rules A20 and A21, which is R tau basically. These are all, including Borel-Laplace, are doubly pinched in the Minkowskian in order to suppress sufficiently the quark-hadron duality violation. For the theoretical expression, in the sum rules, we will use a somewhat improved version of the truncated OPE. For the zero part, as the usual, in the Adler function, in the Adler function, we will use the known coefficients, expansion coefficients, plus in some cases, extension to higher orders, motivated by the renormal structure of the Adler function. For the higher dimension terms in the OPE, for d equal 4, the usual term here, 1 over q to the 4th, but for d equals 6 terms, we will truncate at 6 dimensions. We will use two terms, 1 over q to the 6th and 1 over q to the 6th divided by alpha s, because these two both are suggested by the renormal structure in order to cancel the renormal ambiguity. In the evaluation of the dimension 0 part, we will apply fixed order or Borel resummation with principal value, all in truncated versions. The truncation index, for each truncated index, we will do the fit of the Borel-Laplace sum rules and extract alpha s and the 3 condensates. And the best truncation index will be inferred from the consideration of these FSR momenta, where variation of truncation index should give us a local insensitivity of this momenta. Yeah. And the average value of alpha s will be presented. Now the sum rules, just a short summary. The Adler function is the logarithmic derivative of the quark correlator for U and D quarks. This Adler function you have seen already in the previous talks, already in the talk of Nesterenko yesterday, etc. Now, the sum rules come from the following fact that this correlator is a holomorphic analytic function in Q squared. Q squared is minus square of the momentum. And if we multiply this correlator by a holomorphic function, we can use the Cauchy theorem. For example, in the Q squared plane with radius sigma m, which is roughly mass of the tau squared, in fact, 2.8 g squared. And we get Cauchy theorem gives us the sum rules, where on the left-hand side, we have the experimental parts. This is the weight function. This is the spectral function, Aleph spectral function. Now, Antonio Pic used for G omega, and this was imaginary part, but okay, it's just different notation. And this is the theoretical part with in this theoretical part, we can do integration by parts, and we get this part in terms of the Adler function, and this large G is integral of the weight function. Here we will use operator product expansion in the theoretical part. Now the spectral function, which is imaginary part of the correlator, is given by Aleph. Now in the last two beams, there are strong uncertainties, as already mentioned by Antonio Pic. So we cut them off. Our sigma maximum will be here, 2.8 GeV squared. Of course, here we have m tau squared, which is 3.1 GeV squared, but 2.8. The channel is A plus V, and the theoretical OPE expression is usually for the correlator given in this form, which are simple inverse powers of q squared here in higher dimension terms, and the corresponding Adler function has the similar form, and this is the leading twist or dimension 0 Adler function. Now, the known renormalan structure of the D0 part implies, at least in certain approximation, that the higher dimension terms, higher than 4 dimension, have in fact two terms, two condensates. Not just this, but these ones too, because at least in the leading beta 0, there are double poles infrared, and this corresponds to single infrared renormalan poles. So we will use this expansion, and we will truncate at here the first term, which is the 6th dimension 6. So the corresponding, the corresponding OP for the correlator is similar here also. Now, concerning the dimension 6 Adler function, the first four terms are exactly known up to the for loop, and with some renormalan motivated model, we will do extension to some higher terms, which we will sometimes use in our approximation, in our evaluation. The Borel transform of Adler functions, of course, has this form, and the behavior of the Adler-Borel close to the renormalan singularities has this form. For example, close to the first infrared renormalan, U equal to, it has this form here. This beta 1 or beta 0 are the beta functions here. This is the effect beyond the one loop, beyond the leading beta 0 from the running coupling. But the higher infrared renormalan poles at 3, 4, etc. have here 2 plus this effect. This is at least in large beta 0. So we have here double pole and single pole in large beta 0. So this is something new coming at the next infrared renormalan. Now, this structure and the requirement that the ambiguity of in the Borel integration of these infrared renormalans must be cancelled by the terms in the operator product expansion can be also expressed in the following way, that this imaginary part or ambiguity of the integration over the poles has the same q square dependence as the corresponding OPE expressions. So if we have here in leading beta 0 double pole, this would correspond to this term 1 over, for example, for 6th dimension, 1 over q to the 6th, 1 over a. A is alpha s over pi. And the single pole gives us this usual 1 over q to the 6th. So in addition, of course, we have ultraviolet renormalan poles, which only the leading one we will include here, namely for p equal 1. The construction of the Borel transform, and thus the construction, the generator of the coefficients dn will be done in the following way. First, we introduce the logarithmic derivatives of the coupling, and they are only in the one loop equal to powers, but in fact they are more complicated. Now, if we reorganize our expansion of Adler function d equals 0 in this logarithmic derivatives, we get dn tildes in fact of dn. But knowing dn tildes is equivalent to knowing dn because they are connected with each other. Knowing the first for dn tilde, we know the first for dn, etc., and vice versa. So now if we replace this logarithmic derivatives by powers, we can construct a Borel transform of an auxiliary quantity with d tilde. Now we can check that this d tilde have the renormalization scale dependence. Kappa is the renormalization scale parameter, mu squared over q squared, has the one loop dependence, nothing more. So this Borel transform has simple one loop or leading beta zero renormalization scale dependence. This gives us, suggests, at least in one certain approximation, that the renormal pose of this auxiliary Borel transform have simple powers without beta 1, because there is no beta 1 here, it's one loop. That is, for example, this would correspond in the full BD to this. No? So this is generated once we go from D tilde to D, Borel to D, etc. For example, this term here would then generate the term of this form with here 3, equals 3, when we go from D tilde to D. So the ansatz for B D tilde, which is the generator of the dn tilde coefficients, and thus of all the dn coefficients of Adler function, we take this one. So this is the leading infrared renormal on the next to leading, and this is the leading ultraviolet. In this is rescaling. In this ansatz, we have in fact 5 different parameters. 4 of them are residues, and we can fix them by knowing the first 5 dn tildes or first 5 dn's. Of course, we know only the first 4 dn's, first 4 dn tilde exactly, but for the 5th, that this is d4, which is the 5 loop, we take the effective charge estimate plus minus 63 in order to include a more naive estimate coming from a minimum scheme ansatz for truncated type of Borel of D tilde. So, but most of the other estimates, some of them sophisticated, some of them more naive, are around this value. So we will take this here. Now the values for the parameters in this Borel transform, in this generator of dn tildes, are now, when D4 is, for example, this, are here. The ultraviolet residue is quite suppressed in comparison to the residues of the infrared pulse, and this is rescaling is small. Good. Now, when D4 is 275, for example, dn tilde, they grow according to the renormal structure. In, for example, the ultraviolet effects already become apparent at n equal 5, but for dn, the ultraviolet become apparent only at 10th order. So it does the renormal structure is more becomes apparent more faster in dn tilde than in dn. Now, specific sum rules we are going to use are, this is the weight function for the Borel-Laplace transforms. It is double pinched, and it has this m squared parameter, scale parameter, which we will take in general as complex. The integral of this is somewhat more complicated, and the 2 sides of the mentioned sum rules are now for this weight function the experimental. Here this with the Aleph spectral function. And the theoretical part is more complicated. This is coming from the term 1 of Adler function. This integral over contour of radius sigma m of radius 2.8 GeV squared is coming from dimension 0 Adler function. This is the Adler function that we generate. Just I want to mention that all the first 4 terms are those that are known, and in this model, all others are now generated by this renormal motivated structure. Now the higher dimensional terms of Borel-Laplace are more complicated. Dimension 4 is relatively simple with O4. For example, dimension 6 would have here O61, O611, O612, the two and an additional term here, which this specific function I can show you if somebody asks in the appendix. On the other hand, we will also use as an additional filter finite-energy sum rules, which do not depend of any free scale parameter m squared. These are double pinched momenta, A2n, mentioned already also by Antonio Pic here. Interestingly, A20 and A21 we will use. A21 is in fact R tau, this delta P of the tau decay ratio shown in the previous talk by Antonio Pic. The 2 sides of the sum rules for these momenta look like this. This is experimental part, this is theoretical part, and for A20, the terms are dimension 4 and 6, while for A21, there are only dimension 6 terms, dimension 4 do not enter. The other thing is, how do we evaluate the dimension 0 contribution in the theoretical part of the sum rules? We can use fixed order perturbation theory, which is based basically on the following. The perturbation expansion truncated at certain power of the Adler function, d is equal to 0, and each of those A on the, okay, kappa is usually 1. This is the renormalization scale parameter. Sigma n is 2.8 GeV squared, radius of the circle. And we integrate over the circle this with the weight function. And all these powers on the circle, we Taylor expand in the powers of AK sigma m. This is in this space-like point up to and including this term. Now we can do also another, fixed order perturbation theory using logarithmic derivatives of FO tilde, which is just, we use in terms of logarithmic derivatives, truncated series, and we Taylor expanded this logarithmic derivatives around this point. And the third form will be of evaluating D0 part will be using inverse Borel transform or Borel integral per principal value, going above, going below the real axis. And this is the Borel transform of the renormal and motivated Adler function, singular part, where we just take into account up to certain powers singular and truncate, less singular parts do not include. Since we truncate here, we have to include certain correction polynomial in terms of an, which is also truncated. And this correction polynomial has coefficients which basically have no renormal growth, because almost all the renormal effects are here in this integral. Okay. So results of the fitting are the following. For this full channel of Aleph, we use the Laplace Borel transform, in fact, only real parts. I mean, this has been argued already by Joffe a long time ago that it's convenient to use only real parts, and m squared are rays. usually they should be in the first quadrant. That means m squared, this scales we choose between 0.9, 1.5 GeV squared, and the rays for m squared are real or along this rays complex in the first quadrant. For each ray we of this length, 0.6 GeV, we divide it in 11 terms. So we have altogether minimizing this sum of squares, where delta B is the experimental standard deviations, where we do take into account also the covariance matrix of Aleph, all that is needed there. In this sum, there are 33 terms because there are 3 rays in each ray. And still, when we fit that, what are the parameters that we adjust are alpha S, O4, O61, and O62. We have 4 parameters, and we end up with very small chi squared, in fact, although these are 33 terms. For example, for this ray...
You have 5 more minutes.
Okay, this is the experimental band of Aleph, and fixed order comes it's basically in the middle. His squared is almost 0. So the extracted values for alpha S with uncertainties that we get are the following. For number of truncation, 8 here, for FOT till the number of truncation 5, and for inverse Borel principal value 8. These are the values, central values. Experimental uncertainties are relatively small, but the renormalization scale uncertainties are larger. The uncertainties due to D4, because D4 is 275 plus minus, roughly 60, are large. And variation of truncation, we vary truncation around this, is also large. So theoretical uncertainties are relatively large. Now, how did we choose truncation here 8, 5, and 8 in the Borel summary? For each NT that we get from the fit of the Borel-Laplace, we construct A20 and A21 as a function of NT. This is the band, the experimental band, and we get for FO and PV quite flat curves, and in fact for FO tilde also quite flat, and then it begins to oscillate. And the least sensitivity for FO and PV is around here, NT equal 8, and for tilde FO here 5. That's how we got this. Now, if we don't include the condensates, the dependence on number of truncation is much stronger than here. Here you can see that it's very, very almost constant. So inclusion of O4, O61, and O62 is very important. Okay, these are here the same results that I mentioned here. I also included here contouring proof, but I prefer not to include it in our analysis, but we get much significantly higher value of alpha S. And these are the values of O4 here. And now if we average fixed order tilde and PV, we get this value for alpha S, mostly dominated uncertainty by theoretical values, and alpha S at MZ is this value. If we took, on the other hand, instead of D4 this higher value at the higher edge, about 60 larger, we would get here smaller value of alpha S at M tau squared, and roughly alpha S at MZ would also go down by 4 units. Another thing is, if we took, instead of the 2 mentioned D equals 6 terms in the OPE, the usual D equals 6 and D equal 8 OPE terms in this form, in the simple form, which does not ensure a cancellation of renormal ambiguities, alpha S and M tau squared would go down by 0.008, which would then bring us alpha S to roughly 1183. But as argued, that's not the case here, because what we need theoretically is cancellation of renormal ambiguities in through our OPE. And the other thing is, if we took NT equal 5 in all three methods, that is, if we don't use extension, renormal motivated extension of Adler function, things do not change much. Delta alpha S in M tau goes down by 0.002, and alpha S goes down from 1191 to 1189, so not that much. Anyway, now for the comparison of results, our work for alpha S M tau squared gives us this, which is the closest to, I would say, the work of Pick and Rodriguez Sanchez here, while the works of Boito et al. Are significantly lower. Now, our previous work did not use this improved OPE. This is one thing, and we also use D4 higher, not 275, but 338. That's why in our previous work, we got somewhat lower result, but this is now our result at the moment. With this, I end my talk. Thank you.
Wonderful. Thank you very much. Do we have questions? Yes, please, Diogo.
Hi. I wanted to understand better how you're checking for the consistency of your assumption about the higher orders in the OPE, because you added the dimension 8 and you showed that there is a shift of 0.008, I think, right, to a lower value of alpha S. But how about, I mean, this in your moment, if you do the Borel type of some rules, you would need dimension 10, 12 up to infinite. So what if this is just the beginning of the problem and you would get an even higher correction if you include the rest? I'm asking this because we have seen this problem in the Borel sum rules that Tony showed before. We have checked that, and there is an instability there.
This is a difficult question, because I think since the this renormal unmotivated model can be regarded as an educated guess how to go beyond n truncation 5. No, we use up to 8. But the more terms we take into account, the more, I suppose, theoretical uncertainty we will get. On the other hand, also, if we include more terms of higher dimension in OPE, in general, what may happen is that we may end up reproducing, well, the experimental Aleph results with several terms in OPE, and also with this limited number of terms as here presented, yeah, where we have just 3 condensates. We could have maybe 10 condensates, or it's a not one-to-one problem. That means probably we have several different solutions which are equally good.
Bogdan?
Yeah, thank you for the very interesting talk. I have a curiosity. So you've mentioned at the beginning that you remove the last 2 points with large uncertainties. At the same time, you have pinched weights, which actually suppress the contribution from that area. So why do you actually need to remove those points, and what happens if you keep them?
Let's see. These 2 beans here have very large uncertainties.
Yes, but they are suppressed. Yeah.
Yes. Okay. We didn't think about all aspects, but we do, for example, we do employ also the A20, A21, the usual moments. Okay. I cannot say much more than that.
I mean, the uncertainties are very well under control, just to say this. So they are large, but they are very well understood. They are stat dominated because of the phase space. So I think it would be interesting to see just what happens with all your procedure, because otherwise it's harder to compare with other results because you don't use exactly the same data points. So this is also why I'm asking. So.
Okay, we can include the last two bins and see how the results change and include in our uncertainty this effect. Yes, definitely. Yes.
Thank you. I would be interested to see the outcome. Thanks.
Yeah, okay.
Okay, thank you very much then.
Okay, perfect. So I'm going to be talking about a new determination of alpha S from an improved tau vector spectral function. So how you flip pages here? So I'm going to skip the introduction because Tony Peak already did a good job on this part. Okay, and I'm going to jump directly into the object that contains all the physics, okay, which is the vacuum polarization, okay. And this is the analytic structure of this function. And when you see a picture like this one, you immediately realize that there can be no convergent approximation here. So the OPE cannot be convergent for the simple fact that there is a cut here, and the OPE being essentially a series expansion in 1/q², if it were convergent, it would have to have a disk of convergence, which is, completely impossible when you have a cut. So that means that we have to deal with an object, the OPE, that is not going to be a convergent expansion. And indeed, that's what you also see when you look at the spectral function. The spectral function, has these wiggles, these oscillations that begin with the individual resonances. And as the resonances overlap with each other, you still see wiggles, okay? And once the overlapping is strong enough, is when you start calling it a continuum. So this is why already in 1976, Boito, Quinn, and Weinberg said that, you have to stay away from the cut. You have, to move into the complex plane in Q². So that is the reason. That is the reason why the OPE does not work on the spectral function, on the cut. And it's because it's not a convergent expansion. It's because as all asymptotic expansions is lacking a piece, okay? Oops, okay. All right, so what is it that one can do? If you don't want to, if you want to, take advantage of all the data, the best thing that you can do is integrate over the spectral function. And it's a good idea to put here a polynomial that is going to be a dial, that will connect and disconnect, the different terms in the OPE, as you will see. Then when this scale here is 0 is large enough, it begins to make sense to approximate this function pi of z by the OPE, okay? But of course, you will be making a mistake because as I just argued, the OPE is not a convergent expansion. So it's an asymptotic expansion. So it is missing some piece. So there will be a piece, which is this, what is called duality violations, okay? Let me just move this thing away from here. Oh, they don't see it? Okay. Oh, okay, okay. All right, okay. So then, what you see is that the integral over the experimental data is basically the integral over this contour from the OPE, but there is a contribution from this duality violation piece, okay? And this was the situation, for many, many years. People didn't know what to do with this duality violation. They only had in their minds the idea of Boito, Quinn, and Weinberg to stay away from the cut, from the spectral function, from this region, from the Minkowski value region in Q². Okay, a first step in progress, okay, is that this contribution from the duality violation piece can be written as the integral between the same scale as 0 and infinity of the imaginary part of this function. And so that tells you that the duality violations have something to do with the behavior of the data on the cut. And if you have information on that, then you can extract some information on the duality violations, okay? Needless to say, in the OPE is where alpha S is sitting, and that is, the object that we would like to determine. So this doesn't move anymore. Page down, doesn't move. No, it doesn't move.
We see the mouse pointer.
What?
You were moving the mouse pointer on the screen that was projected. That was visible.
Yes, but I couldn't flip the page.
Ah, okay, that's bad. Okay.
Try again.
Doesn't seem to work anymore.
So this.
Oh, that's the one that works.
Those work.
Okay,
Sorry.
okay. It goes the other way. All right, so here we have again our finite-energy rule in terms of the piece that comes from the OPE and the piece that comes from duality violation. So what do we know about this? What we know is that if we choose for this polynomial function W of t a moment, a power t to the n, then this essentially selects a contribution from the OPE that comes from the corresponding condensate, which is this, with the power n, you have the condensate 2n plus 2. But now we have to realize that since the OPE is an asymptotic expansion, we should refrain from the temptation to think that this is going to go to 0 when n goes to infinity. In other words, that just because the scale is 0 is large, this is not a suppression, right? Because in an asymptotic expansion, you should think that these coefficients here are going to grow. Naively, a simple example would be they are going to grow exponentially, okay? So this is no suppression whatsoever, okay? And it's a good idea in an asymptotic expansion to stay in as low orders as possible. Now, because the OPE is asymptotic, there is this piece. If the OPE were convergent, then there would be no duality violations. And if the OPE is given by these powers here, you see that these powers contain no imaginary part whatsoever. So that means that the imaginary part, is given by perturbation theory and duality violations directly, okay? Now, what do you expect, for this contribution from duality violations? Well, being the OPE asymptotic, you could draw, an analogy with what happens with renormalants, okay? Which the usual perturbative expansion is also asymptotic. The coefficients are believed to grow, factorially, and that the series, the perturbative series, misses an exponential contribution. Exponential in what? Exponential in 1 over alpha. But that is for an expansion which is in powers of alpha. So for an expansion which is in powers of 1 over q squared is going to be an exponential, of minus q squared, minus t times a coefficient. So that's, in general terms, that's what you expect for the behavior of the duality violations, okay? Now, what did people do so far? Okay, so people, follow what is called the pinching strategy, which is, if I want to suppress this integral here, this duality violation contribution, what I can do is choose a polynomial which precisely has a 0, which precisely has a 0 at a 0. So because that's precisely when the amplitude is the largest, okay? And that qualitatively makes some sense. However, you have to realize that, if you put more pinching and you want to suppress more these duality violations, that comes at the price of having, a higher degree polynomial. But if you have a higher degree polynomial, then this n is large, and then you are switching on, the contribution from higher and higher condensates that grow in principle factorially. Okay, higher condensates contribute. Okay, and these higher condensates, you don't have a clue of what they are. So this is one of the main theoretical messages that I would like to, come across in this talk, which is that with pinching, there is a very big price to pay, which is that you cannot, simultaneously suppress duality violations and the condensates. If you suppress duality violations by using a lot of pinching, that means that your polynomial is of higher degree, and therefore there will be a contribution from a very high dimensional condensate, okay, which in an asymptotic expansion is going to be big. It's not going to be suppressed. So there are three things that you have to do before you get to a possible determination of alpha S, okay? One is, what do you do with perturbation theory? What do you do with the operator product expansion? And what do you do with duality violations, okay? So what do we know about perturbation theory? So I'm going to treat perturbation theory as, in a little abuse of language, as the condensate of dimension 0, okay? And thanks to the work by Bykov and company, we know this expansion are to power, alpha S to the 4th. But we're going to use just, as a check, a guess estimate for the power alpha S to the 5th, with a value of C51 given by this thing. Actually, this we can, turn it on or off and see, how much, the result depends on this coefficient. But we still have to decide one thing, okay, which is what mu are we going to use in this expression, okay? And so there is the usual choice, which is just choosing mu equals to a 0, which is the scale that is going to appear in the finite-energy sum rule, and that is the usual MS bar choice, okay? Which in this business goes by the name of fixed order perturbation theory, but it's nothing but the usual MS bar. There is another choice which is unconventional, which is choosing mu, not only a complex number, but the complex number that is changing as you go along the contour, okay? And it is unconventional because it's the only place where this choice is being made, okay? I would like to argue that these two objects, the perturbative expansion that you find in CIPT and FOPT are two different objects, because I mean, is this CIPT the one that should be compared with the alpha SMS bar that you extract from Z going to QQ bar? Because in Z going to QQ bar, people do not use any circle at all, okay? They just stick, to the MS bar prescription. So that would mean the FOPT prescription, okay? Even though, and if anybody is interested, I can show it. Even though there is a way to express the decay of Z going to QQ bar in terms of a circle. So there would be a CIPT version of it, but nobody's using it. So what's the point in comparing, the alpha S CIPT from tau with the alpha S that you get in this case, which is actually FOPT? I'm not talking about whether it's numerically relevant or not. It's a conceptual thing. I think that these two objects are different, okay? And moreover, and I'm sure that Andre Hoang is going to talk about this. It so happens, after a paper by Hoang and Regner, that the Borel resummation implies actually a mismatch between CIPT and the OPE. So the OPE is not really consistent in conjunction with the CIPT expansion. So that means that we're going to use FOPT. So that means honest to goodness MS bar. So that was the perturbative part. What about the OPE? Well, we're going to use 4 linearly independent polynomials of degrees, smaller or equal than 4, and no linear term. And that's because, there is some evidence based on renormal models that this creates, problems with the perturbative expansion. And so these are the 4 polynomials, okay? And as you can see, the first polynomial has no pinching. So this is going to be very sensitive to duality violations. The second one is singly pinched, okay? So, and it has a single zero. The third polynomial is doubly pinched, and the fourth polynomial is again doubly pinched. And this combination is good because it's going to allow us not only to check, the effect of duality violations, because all these polynomials feel duality violations differently, but also it's going to allow us to cross-check, the values that we extract from the condensates, because, you see that C6 participates in these three, okay? So that's a consistency check. Moreover, we also have to say what we do with duality violations, okay? And so this is the simple form that we're going to use. But let me make it clear, okay? This simple form does not come out of the blue, okay? This simple form, in this paper, we work out, this expression with this result. Is the result from assuming asymptotic Regge behavior in the spectrum at large n, okay? This assumption is not an assumption in two-dimensional QCD. Is it a fact, okay? And in four-dimensional QCD, there is some phenomenological support for it, and is in agreement with known properties of QCD, like for instance the string picture, okay? But notice that it does not have any positive powers of S. So the table that you saw in Tony Peaks, with the positive powers of S, doesn't make much sense from this point of view. By the way, I also uploaded this paper in the Indico. So if anybody's interested, can look at it, okay? So with this expression, we have, 4 new parameters, okay? And so besides alpha S, we'll have to determine these 4 new parameters. So what do we have? So we have different degrees in polynomials. That will give us the possibility to cross-check the values of the condensates, which is a check on the OPE that we're using. We also have different degrees of pinching. So that's a cross-check on the values of the duality violation parameters, which is a check on the duality violation parameterization we are using. And there are no issues with neglecting contributions from condensates, unlike the truncated OPE approach of these two authors, okay? And this will be the subject of Maarten Golterman's talk, later on. So that was theory. Now it's the time for data, okay? So these are the spectral functions determined by Aleph and Opal in the vector channel. And you see that the vector channel is dominated by the decay into 2 pions and 4 pions, but that there are residual channels which are important. You will see that are important for alpha S. And most of the residual channels, if not all of them, are actually determined using Monte Carlo, so not real data. So this is something that we're going to change. Using E plus E minus, we're going to be able to replace these residual channels, which are Monte Carlo determined by real data. And we're also going to, combine, the 2 pi and 4 pi channels from Aleph and Opal, okay? So the combination of these two channels, 4 pi and 4 pi channels from Aleph and Opal, will follow, the algorithm used in our data by these 3 gentlemen. And we know that combining data is always, advantageous, okay? There is no more Monte Carlo. So the 7 residual channels are going to be determined from E plus E minus using conserved vector current. In the region where these residual channels lie, isospin breaking is very small because there are no narrow resonances. And we are also going to profit from some data from Babar on this particular channel, plus updated of all the branching ratios. So this is the result that we obtain. So we see that the red points are the original Aleph data, the green points are the original Opal data, and the blue points are the result of all these analyses. On the right-hand side here, you see the value of the local p-value, beam by beam, and all the chi-squares are good, okay? And what you see is that there is a dramatic error improvement near the endpoint here in this region. Again, the same spectral function where you see the total result in the green points. The blue points are the dominant channels, 2 pi plus 4 pi, and yellow is the residual, okay? On the right-hand side, what you see is that indeed all the residual channels basically pile up near the endpoint. So results. So this is the result for alpha S that you obtain, for instance, from the finite energy sum rule with the polynomial 1, okay? And what you see is what you expect. You expect that, you know, for S mean very low, okay, our description of duality violations is not good enough. Remember that it was supposed to be valid only asymptotically for large S. It's not good enough, but there is a point at which the thing stabilizes, okay, with a very nice plateau, okay? And then, you know what happens is that you run out of data. So therefore the errors grow, okay? The values of the results for the p-values that you've obtained in these fits are extremely good, more than 45%. Now, this is what you are, what you are actually fitting. Okay, so the left-hand side is the experimental data. The right-hand side is the OP plus the expression for duality violations that I showed you. And now you can compare. You can, in this plot on the left-hand side, what you see is the black points are the experimental data. The red curve is the result of the fit, including duality violations. And the green curve is what you would obtain if you neglect duality violations. It is clear that the data prefers duality violations. And also, now that you have a determination not only of alpha S, but also of the duality violation parameters, you can go and compare with the spectral function itself. And that's what you obtain on the right-hand side, okay? So again, you see that the red curve does a very good job. The green curve fails completely because it lacks duality violations. Now, you can repeat the same exercise, but now, with using different moments, like, different combinations, W0, W2, W0, W3, etc., several fits, single moments, combined, all sorts of combinations, right? This is good because it allows you to check, for instance, the value that you obtain from the condensate of dimension 6. And at the same time, it also allows you to check, that the duality violations are under control because all these moments fill the duality violations in a different way. Now, from this, we obtain this value for alpha S, okay? Where we have, the statistical error given by this, we take it this one. And this here, contains everything you can think of, like, perturbative series truncation, scale variation, and even, the effect of duality violations, which, you can measure, like, for instance, from the difference between these two numbers or these numbers, okay? Okay. So summary and conclusions. So if you run this value of alpha S and the tau mass, you run it to the Z mass, that's the number that we obtain. And for those, diehards who still, want to see the number in CIPT, in the CIPT version, that's the number that we would obtain. On the left-hand side, what you see is the plot with, in which alpha S was obtained, from OPAL data, which is something that we did in 2012. The result from the Aleph data, and this red point is the result of this work. The blue point, E plus E minus 2 hadrons, will be the subject of Diogo Boito's talk next, okay? So our conclusions is that we have a new vector spectral function from tau decays without any Monte Carlo input. So far, it's only data, okay? Can we do better than this? Well, to be able to do better than this, it'll be very helpful if we have more precise data on the main channels, 2 pion and 4 pion, and this could come from Bell 2. It would be very nice if we would have this input. Regretfully, there is no such possibility for the axial channel for obvious reasons, right? Because there is no axial photon, okay? And just, you know, as a side remark, but important to keep in mind, these finite resolution rules are dominated by perturbation theory, but non-perturbative effects are crucial to really pinpoint the value of alpha S. So, and let me just finish by showing that the stability that I show you for alpha S is not only for alpha S, but for all the parameters that we have in our FET, including the duality violation parameters. And that it so happens that, you know, these two parameters here can be related to, you know, standard values for the parameters that you find in a ratio description of phenomenology. And they agree very well, which I believe is a non-trivial check. So thank you.
Thank you very much for this nice presentation. Do we have questions? Yes, Tony first.
Okay, I appreciate the effort you have done improving the spectral function. I think this is something very valuable. But it is obvious from my talk, I'm not happy at all with your treatment of duality violations. So let me explain why. I don't complain whether your answer is well motivated or not. Okay, it can have a very good motivation in the asymptotic regime. The problem is that you are applying this answer at 1.2 GeV. And there is no motivation whatsoever from theory to defend this particular parameterization there. In fact, even some of your approximations in the paper where you try to defend this parameterization with rigid theory, you use approximations which are certainly not valid at 1.2, 1.3, 1.4 G. So there is a systematic uncertainty that you are not implementing in the game. You should analyze how sensitive the results are to the particular ansatz you are adopting. And as I have discussed in my talk, the sensitivity is very large. So you are missing a systematic uncertainty all the time. Your values of alpha S are reasonable, which is just tell us that the tau is providing a very good determination of alpha S. But you are missing a systematic uncertainty that is very important.
Okay, so maybe you can reply to this point, but I would say that then we really postpone discussions to the end. But
yeah,
now
I
if
should
you
be able to reply.
yes,
right?
indeed. Please
okay.
Reply to this.
Well,
but then
yeah. First of all, as you can see in this plot, you know, your 1.2, I don't know what it is, because here I see a 1.5, 1.6, which it could go all the way to 1.8. Okay.
That's energy square. My 1.2 is
yeah.
energy.
But why don't you keep taking square roots, and in the end it is going to be 1? Okay. No, I mean this is not a valid point. And then on top of that, let me just tell you something else. Okay, you have criticized in your talk this expression for the duality violations, but people should know that this is exactly the expression you use in B minus A. You use exactly this expression in B minus A. So tell me why you can use it in B minus A and not in B and A.
My use of this expression has been completely different. It has been only to assess a systematic uncertainty varying parameters and not to make any precision determination of a strong coupling. I am talking about systematic uncertainties. I am not complaining about a particular parameterization. I am just asking why you don't include the systematic uncertainty coming from the particular parameterization.
okay, maybe
if you use it to evaluate the error, that means that you trust it at least for that. So you could also use it to evaluate the central value.
we continue the discussion later. Anna, do you have a question to the talk or a point for discussion session later, Andre?
We can do it later because it is a similar.
Okay, so maybe it's better to postpone this. Okay. Yes, thank you.
So let me start by thanking the organizers for the opportunity to give this talk. So I am going to talk about alpha S around the tau mass scale, but let me just a second here. Yeah. So I'm going to talk about alpha S around the tau mass scale, but using E plus E minus 2 hadrons data. So this is really R of S data. So the type of data that goes into the determination of G minus 2 of the mu on the inclusive E plus E minus cross section. So this this work has been published in 2018, essentially. So there will be some discussion of what might have changed, but not much changed. So this was done in collaboration with Maarten Golterman, with Kishavazi, Mautman, Nomura, Peris, and Toivna. Is everything all right? Okay. You hear me, right? Is everything all right? Do you hear me? I hear noise.
Everything fine.
Okay.
There's some strange noise.
Yes, I hear noises. Is this from me or?
I don't have the impression.
Okay, I'll try to continue. So I'm going to talk about this determination that is done at lower energy. So it's around the tau mass scale. As I'm going to discuss, it's not exactly on top of the tau mass scale. We're a little bit above the tau mass scale, although we're going to quote results at the tau mass scale because that's where people have some sort of an intuition for the measurement. So this is a determination that is done at lower energy. So there's the advantage of being more sensitive to the QCD coupling, with perhaps the disadvantage of the fact that you need to control non-perturbative physics, which has been actually the subject of the discussion in the last talk, and some of the problems that appeared in Tony's talk as well. So I'm going to talk specifically about this determination of alpha S, which is in the PDG average. So that's the one I'm talking about, is Boito 2018. And this is what the PDG now calls a low Q squared determination of alpha S. So we're using R of S data. So this is the usual ratio of the cross-section plus or minus 2 hadrons divided by plus or minus 2 muons. We're working with the combination done by Kishavazi, Nomura, and Toivner. So here I'm going to call them K and T. So they're going to appear in this talk as K and T. Obviously, we could do the same work with other combinations, in particular DH and Z. If we had them, we could try it and see what we would get. I don't expect big changes, but it's also an interesting exercise that can be done in the future. I should remind you that this is a combination of many data sets. So they combine this to the statistical procedure to then get what in this plot is shown as this yellow line here, this yellow band. So this gives the combination of the data. This is the ideal thing if you need to integrate the data. And as I'm going to discuss, this is the best thing to do, to integrate the data, precisely because individual measurements of R are not precise enough to get alpha S. So if you look at papers that measure R, they often give some sort of an estimate of alpha S, but this estimate has very large errors because individual measurements that you see here, for example, in these data points from the CADO collaboration, they have large errors. So here, this dashed line is perturbative QCD. And perturbative QCD, you would have to move a lot alpha S to reach this 1 sigma here. So if you try to extract alpha S by looking locally at R, this will never give you a good precision. So you need to work with integrated moments. So here, this is a choice, but it's the right choice. In tau decays, this is mandatory because there is a neutrino, but here, this is the right thing to do if you want to get anything that is more or less precise. So I'm going to show in the end that it's not as precise as tau decays, but it's a nice cross check. So I'm going to do the same type of some rules that has been discussed by Santi and by Tony. So there is no new thing here. And also all the talks actually before me discussed that. So I don't have to go into the details. All the details of the theory have been discussed in the 3 talks before. I just want to specifically say that we're going to use then the KNT data. It's not exactly the KNT18 data. I'm going to say what's the difference in the next slide. In the theory side, there's slightly different compared to tau decays because here you have the electromagnetic current coupling to the photon. So we also have isospin 0 and isospin 1. So here we have 2 isospin channels, and we have the S quark, which can be separated in the tau decays. You have the non-strange decay rate. Here we don't have that. So we're going to have to consider the mass of the strange quark. So this is the data we're working at. I'm going to start by discussing the data. So as you can see in this data set, so this is, as I said, this is essentially the KNT combination, but it's not identical to the KNT18. And I'm going to discuss why. So you can see in this data that there is a large density of points in this region and very few data points in this region. So what's going on here is that you have this transition between the exclusive region and the inclusive region. In the exclusive region, you measure individual exclusive channels for the E plus E minus cross section in hadrons. You have to measure all these channels to then add up and then get the exclusive measurements. And in the inclusive regions, you do an inclusive measurement. So in the K and T original combination, the transition between these two was at a lower energies. But for us, it's convenient to push this as much as possible. So now the transition in our data set is at 4 GeV squared, so that we have a larger window here above m tau squared with a high density of data points, so that we can exploit this window that is above m tau squared to do our fits. And I'm going to discuss what happens if you go in this region here. So it's quite clear already that you have much less information in this region. You have not that many data points. They're highly correlated and the errors are not small, quite large. So this means that, and also the sensitivity to alpha S is much lower here. So this means that the precision that you get is essentially determined by the left-hand side region of this plot. So going to this region won't add much, and this is something that I'm going to discuss a bit more later. So to give you an idea of what happens once you integrate the data, so we're going to always work with integrated data. So our sum rules are going to be, the experimental side is an integral from threshold up to a value that we call S0. So we're going to integrate all the data up to S0. I'm showing here a comparison of R measured at 4 GeV squared. So if you take a typical value of R around 4 GeV squared, it has about 4% error, 4.3 here. And we're going to work with the same weight functions that were presented by Santi, the talk before mine. And with these weight functions, you get these values. So in one of them, for example, here you can see this is the kinematical weight function. You can see that you get an error of 0.6%, which is significantly lower than that. So that's the main reason why you have to do sum rules and integrate all the data if you want to get precision, anything that is precise. So the theory has been discussed quite a lot already in the talks before me. So I can summarize it very quickly. So perturbation theory is essentially the same because perturbation theory is calculated in an expansion in the quark mass. So it's the perturbation theory is for massless quarks, and we know it up to alpha S to the fourth, thanks to the work done in Karlsruhe that has actually later been checked also at NICHAF. Then we have also to include the OP condensates. And here we have to consider mass corrections. I'm pretty sure that all talks before me didn't include the mass corrections because they're tiny for UND, but for the strange quark, you have to include them, and this is known up to alpha S to the third. Then there is an electromagnetic correction. This is very small, but we add the leading one. And then there are the duality violations, which are essentially what Santi showed before. There is some difference here, so I'm going to discuss just a little bit about perturbation theory and a little bit about duality violations in more detail, but it's going to be very short. So about perturbation theory, this has already been discussed as well, the problem with the FOPT and CIPT. The same thing will happen here, because if we do this sum rule, we're going to have to integrate our theory in the contours, or you're going to have to make a choice. So in principle, the problem exists here as well. But I am not going to discuss in detail the results that we get from CIPT, because as you're going to hear in the talk by Andre, recent work has shown that there is some potential issue with CIPT. Because it seems to be incoherent with the usual treatment of the OP. So it becomes dangerous to use CIPT and then mix it with the FOPT. So the clean thing that we can do is to use FOPT only, unless we have some good prescription to fix CIPT. So my results are mainly FOPT. I'm going to show them results in FOPT and only once in a while say what I would get in CIPT. However, I should say, it's a comment that I should make, that the discrepancy here is smaller than in tau decays because we are at higher energy. So the difference between the two is smaller here in the E plus E minus. So about the duality violations. Here the situation is slightly different compared to tau decays, because in tau decays you have only isospin 1. But here you have isospin 1 and you have isospin 0 and you have the strange quark. So you have all of that. Isospin 1 and isospin 0 light quark connected components are, if you are away from the resonances, it's reasonable to assume that they are essentially the same, that because of isospin symmetry, it's okay, and certainly a very good approximation for our purposes to assume that they are the same. So then here we can get info from this part, this 5/9 times this function, we can get some information from tau decays. And if you want, you can include this information in the fit. It's actually necessary to include some information from tau decays in the fit, because if you want to fit all the parameters that you have in duality violations here, you cannot do it because the data are not precise enough. So here we have also this other component. So this component that has essentially the strange quark. And we cannot expect the duality violations to be the same, because here you have the mass of the quark, the resonance masses are different, and so on. So we need to include this as well. And we cannot fit everything from the data. So what we do is that we need to make some assumptions. So our description of DVs here contains some assumption, additional assumption, which is that in the blue part, which is mainly a strange quark, this was going to amount to a shift in the duality violation. So we have two parameters in the blue part that are fixed to their I equals to 1 value, essentially. And then two of them, which are alpha, which are so we fix beta and gamma to their values. This is what's written here. The I equals to 1 values, and then we fit for the others, alpha and delta. So it gives you a shift. So that's the situation with duality violations. However, I'm going to show that here that duality violations are not so large if you go above the tau mass. So here in the results that I'm going to show, duality violations give a smaller contribution. It's less important, and we're going to use them as some sort of a cross-check that the result is under control. But they are less important here because of this exponential suppression. So we work above the tau mass squared only. So we're always above the tau mass. So I'm going to go to the fit results. So as I said, the moments that we're using, the weight functions are the same that Santi showed before. So we have here this W equals to 1, which is an unpinched moment that is sensitive to DVs. What you would like to have are moments that have a good perturbative behavior, that are, so it meaning that there is some sign, some apparent sort of convergence in the theory, the perturbation theory. You want to have a small contamination from condensate contribution, so it's not nice to truncate the OPE, because this has been shown to be problematic, and there can be a systematic uncertainty from truncating the OPE at lower orders. And you would like to suppress duality violations. I mean, it would be good if you could do all of that, but you cannot do all of this at once. So you always have to make some sort of a compromise. So in the W equals to 1, the compromise is that DVs are not suppressed, but the other properties 1 and 2 are very well satisfied. In 1 minus y squared, you have some suppression of DVs, but you start getting some OPE condensates. In this one, which is a kinematical moment, now you have two condensates that you have to include in your analysis, but it suppresses much more the DVs and so on. So there's always a compromise. But we check for consistency, we check that the results are rather stable when we change the moments or do combinations. So the choice of moments is the same that Santi presented. So the strategy, the general strategy, is very similar to what we did in tau. So I'm going to discuss quickly how we do the fit. So this is the typical fit result. I'm going to show this for several moments. So there are here the 4 moments. What we do then is to integrate the data. This is in red. So we integrate the data, we get a red data point, but we're going to do this at several values of S0. And we're going to fit all the data points that are in between these vertical blue lines. So the fit is done in between the vertical blue lines. I'm showing m tau squared here. So you see that we're always above m tau squared. So all the fit is always done above m tau squared. And then we can check for other moments what happens in other moments. We have always reasonable p-values, no surprise, nothing that is very strange. In the fits that I'm showing here, there is no DV. So the DVs are not included here. And they're not included here because we have added them and we saw that they're not very large. So this is something that I'm going to show quantitatively in a moment. So if you change your moments, you get something that is, again, very decent. And the alpha S values are all consistent. So these are the alpha S values that we get in FOPT, as I said. So we get something that is around 0.3 with an error that is larger than what you get in tau decays. So we have an excellent consistency between the different moments. The OPE coefficients are also consistent. I don't have a table with them here, but they are all consistent when you have d equals to 6 in this moment and in this moment and in this moment, they are all turn out to be the same. The errors here are a combination of statistics and an error from the fit window. What I mean by that is that you can move these boundaries and alpha S will move a little bit, but this gives you a small contribution. The error is largely dominated by the data. So the error that comes from the data, so the error that comes from the data. And the error in the data, of course, includes everything, statistics and systematics. So if you don't want to call this statistics, you may call this error from the data or from the experiments. And here the errors from the data are larger than what you get in tau decays. I'm going to give a breakdown carefully at the end. So if you use CIPT, you would get something like 0.304, so it's slightly above that. so systematically above. So this is what we also see in other analysis. It's above. However, it's the difference is smaller than what you have in tau decays. So this plot is the plot that I promised to show that the duality violations are not so large here. So what I'm showing is the value of alpha s at m tau squared obtained in these feeds, in several of these feeds, using different moments. So in green, blue, and red, I'm showing the results from the first 3 moments here, in green, blue, and red. So you get the alpha s from these moments. And then I'm showing the results for one of these moments, including duality violations with some information from tau decays, as I said, using some sort of a prior in the fit that takes all the correlations and covariances into account and adds the information that we have from tau decays. The information that comes from tau here is from the analysis of the Aleph data. So now you have here m tau squared shown. And what we see is that if you go to larger energy, so you do the fit, what I show, every point is plotted against S0 min, so the minimum value of the energy that enters the fit window. And you see that at larger energies, everything agrees rather well. So the different moments and with or without TVs, everything is more or less in good agreement. If you start lowering the energy at some point, which actually happens to be around m tau squared, the things depart, and then you have a result that is stable if you include DVs, and not so, and it starts to be rather unstable and go to values that are too low if you don't include them. But as long as you are above m tau squared in the larger energy region of this R of S data, then everything is safe. And you can use DVs just as an estimate of an error associated with them. So then here, the DVs don't enter our central values. They enter only as an estimate of the size of the error. So I wanted to make some comments about the data above 4 GeV squared. So everything that I showed here before was up to 4 GeV squared, so this line. So all the fits stop here in the transition between exclusive and inclusive region. So the data in the inclusive region, the first thing that we checked is that the data is reasonably compatible with perturbation theory. So the test that we did here is the following. In blue, you have the data. So in blue is the KNT data that we use. So the data that KNT actually produced for this paper. So this the one that transitioned at 4 GeV squared. So the blue is this data, the red line is perturbation theory, and you can see that it's slightly systematically above perturbation theory. You should not forget that this data is highly correlated. So in fact, you don't have all these data points that are there. You can see that the points barely fluctuate if you look at nearby points. So you don't have that much information in this data. So if you generate toy data sets using the covariance matrix, and that's what we do in orange, you basically see that you can get many things. You can get something that is looks visually more compatible with the perturbation theory. That's what we see on the right-hand side. So this suggests that the data, although it is systematically sitting above perturbation theory, it's not incompatible with perturbation theory. However, if you start doing fits in this region where you have less data with larger uncertainties and less sensitivity to alpha s, you don't get much information. Alpha s fluctuates with a larger error, and you don't conclude much. So that's unfortunate in a way, in a sense, because you would like to go to higher energies where things are in principle better behaved. But at the moment, it's a little bit inconclusive because you go there and you don't get much information. So this is a small update of the situation. The small update is that now there is BES3 data that appeared in December. So of course, none of this is included in any of the results. This is very new. The gray dots are the data that we used in our paper, this modified KNT data set. And in magenta, you have the new data from BES3. So this new data from BES3 are significantly above, in these 2 data points, above perturbation theory. So again, there is some sort of a tendency to be above perturbation theory. It's not completely clear what this means. We don't have that many data points. We would need to get a new combination of the data to rerun the analysis, but there seems to be some sort of a tension with perturbation theory. It's not so easy for perturbation theory to reach this magenta points. So the situation here with the not so many data points and with 1 or 2 data points from BES3 with small errors is inconclusive, remains inconclusive. So that's what I wanted to say. So there is this issue with inconclusive data above 4 GeV squared. So here, the scale here is in GeV, and be careful. So I'm going to show the final results. So this is the final result for alpha s at m tau squared with a FOPT. So this is the data uncertainty, which is the dominant one. So the value is essentially 0.3. And then we have a data uncertainty of 0.016. DVs give a contribution to the error of 0.005. Then there is a contribution from truncation of perturbation theory, which is rather small. And we get this value. If you evolve this to MZ, and this is what I show in the left, you get 1158, which is somewhat low, but with an error that covers it covers it can touch the world average easily. I'm comparing this to what Santi just showed from tau decay. So our newest analysis from tau decay from 2021 with improved spectral functions. So we get this value here, which is a little bit above, and with the narrow that is essentially half of what we get here. If you do CIPT, we would have 1165 here, while in tau decays you have something in front, so I can't read the number, but I think it's 1191. So you can see that the discrepancy is larger in tau. So let me finish with this comparison. So this plot has essentially been shown by Santi. So this is the result that I'm discussing in this talk. So this is the red point, and then you have the blue point that was discussed by Santi. Santi's result is not in the PDG average, not yet. It was not included. So these two are in the PDG average. So these are the ones where we analyzed OPAL data and Aleph data separately. So those are there in that first plot that I showed from the PDG. And I also wanted to add the result that Vicen presented yesterday, which is done at slightly larger energies, but also not so high. So this is essentially, this is only charm sum rule analysis with no input from lattice. So this is pure experiment as well. And you can see that they're all in good agreement. They're all fixed order here. They're all in good agreement. And all of them in good agreement with the world average that is shown as the yellow band. So the conclusion is the following. So the results that we get from a plus and minus are robust. So they have a small contamination from duality violations because we can go to higher energies. The errors are dominated by the data errors, which is in principle good because you could, in principle, reduce this error. It's not completely clear that we're going to have data that is much better, but you could, in principle, improve it. We have then an independent cross-check. This is a very independent cross-check of the tau measurements because the data is completely uncorrelated. The data at higher energy is still scarce. What happens with the data if you include the data at larger energies? It's still unclear because there is this not that many data points. Errors are quite large. Some of them are slightly above perturbation theory. So there is some issues there that is not completely. It's not very easy to make a proper statement about the data above 4 GeV squared. And everything turns out compatible. And if you want to know that, the difference between FOPT and CIPT here is smaller. That's it.
Thank you very much for this very clear presentation. Do we have questions from the audience here or from Zoom? I see a hand by Bogdan first.
I think Klaus was first.
Sorry, Klaus then, sorry.
Okay, so I have a question to your data uncertainties. You nicely explained about the correlations and lack of fluctuations. So I'm really wondering how you can gain something in uncertainty when all of these points look like they are 100% correlated in terms of uncertainty.
So you're talking about this transparency, right?
Well, not only this one. So this one here, you explained nicely, you add one or another point to the right, which is very correlated to the previous ones, and you don't gain much information. This is logic. But here, if I take all the gray points, to me, it looks like you can replace them all by 1 point. Provocatively speaking.
Yeah, by 1 point, I think it's a bit radical, but I believe that if you could definitely do clusterize the data with less points, and I don't think we would lose much information. So I don't think, I think we are agreeing on that. I mean, there's lots of correlations here, so you don't have all the information that this many gray points might suggest. And this is something that we see in our fits, because when we include that, we don't gain much in terms of uncertainty when we include these points.
Do you have a representation visually of the correlations? So kind of correlation matrix or so that could be useful?
I don't have a visual representation of these correlations. No, I'm sorry.
Yeah, but that could be very helpful diagnosing the impact of new data, hopefully less correlated, etc.
Yeah, the BS3 data, they always have some correlation, right, because of the systematics. So this information is given in BS a bit indirectly, but it's given in their paper. So you can, if you look there, they have like 8 sources of systematic uncertainty. They say which ones are correlated, which ones are not. So you can work out the correlations of the data. They are a bit correlated as well, but they're not highly correlated.
Okay, thank you.
Thank you, Bogdan.
Just an immediate follow-up on this point. I mean, if you look at the light gray points, I mean, those are results of interpolations and fits. So they are with finer steps than the original data points, and this is what explains the strong correlations. But even the data themselves are dominated by some systematic uncertainties, and they still have strong correlations. So Diego, thank you.
Wait, Bogdan, just make a comment that this plot doesn't show all the data, okay? Because I mean, this is a bit misleading. I just showed the data with smaller errors. So there's more data that I'm not showing, which might be the justification for having more data points. But you're right that if you look at this plot might be a bit misleading because not all of the data are here.
In that procedure, there's some clustering, there's some interpolation. I think this is why you see the points aligned. I mean, it's still related to that, even if originally you have more points. My comment was on something else. So first, thanks for having mentioned also our combination. I wouldn't say our data, our combination. And I have a comment. So it is a known fact that in the combination that you use here, there is one important systematic uncertainty missing in the 2 pi channel from the Babar-Chloe difference. So this is really dominant in the case of G-2. Have you looked at how important it is for the moments that you mentioned here? For G-2 is the dominant systematic.
So what I can tell you is that, so probably KNT would have definitely a much better answer than I have, because this part, obviously they are the experts on. I can tell you that these data is exactly in the status of the 2018 data. So anything that they checked later, for example, in their 2019 paper and discussions that happened after that, we have not included in this analysis.
I see. I mean, it was not used. I mean, this was not taken into account in either of their studies. So this is something that doubles the uncertainty essentially in this important channel. And then for the region between 4 and 6 GeV squared, if you look at the combination plot, I think you've shown this on slides 5 and 7.
Beginning.
Yeah, so there you can see a systematic shift of the combination result, where the one where you also have the data. I think it's maybe on slide 7. No, I mean, so I'm interested in the region between 4 and 6 GeV squared, where you also show the data. Yes, but also with the data, with the data.
Oh, with the data. Sorry, the data points from the actual experiments.
Yes, yes, exactly, exactly. Yes, because you can see that here the combination is shifted towards the less precise points, which can be quite surprising. And it's something we have also pointed to in the G-2 discussions.
Yes, so yes. I think, I mean, you know that this is related to long distance correlations, probably coming from the fact that the BS data extends up to the charm region and so on. So
yes, but there are some assumptions there.
Yes, but I think there are, of course, because they do this very non-local combination and they take into account everything. So all the correlations are included and so on. But however, we use all the we take all the correlations into account, and this precisely the fact that they are a little bit above can be just a fluctuation because they're so correlated, as we show here in this toy data sets.
Yeah, I mean, it comes with some assumptions that you really know perfectly the correlations.
Bogdan,
this was, yeah.
We're running really late. So
sorry, I stop here.
One last question by Tony now, and then we'll move on.
Yes, you are saying all the time that you are extracting alpha S from much higher values than the tau mass, but unfortunately, for reasons that you have explained, you are just at the tau mass and a little bit above. Then I am surprised by some contradictory statements that you are making, because here in this slide, you say no duality violations, but then in slide 17 and in the summary, you say the duality violations are very small and they can in fact be neglected above 3.2 GeV squared. 3.2 GeV squared is 1.788 GeV. The tau mass is 1.777 GeV.
Yeah,
so to say that at one point you can neglect duality violations, while at the tau mass duality violations are very, very important, is contradictory. One of the two statements cannot be correct.
So, so the first thing is that I might be wrong, but I don't think I said we are working at much higher energies than m tau. So I don't think I said that. So we can check in the recording later, but I think I said we're working at higher energies than m tau, which is a fact, right? Then of course you might say you're not at that much higher energies, then it becomes a subjective discussion, but we are necessarily above m tau squared in all our fits. Then I agree with you that there is some sort of a transition, right, where duality violations are more important and they become less important. At some point, they're very important. At some point,
No, but put the slide 8.
Sorry,
Put the slide 8.
Is around where it happens. That's all.
No, put the slide 8, please.
Sorry?
Can you put the slide number 8? Okay, the tau mass is just in a broad isoscalar resonance. In fact, it's a combination of an omega and an phi resonances, which are not there in tau decay because tau decay is a isovector. Therefore, the problem you have here, the tau mass, and in fact, you have this problem also above the tau mass, is not present in tau decays. And if duality violations are negligible at 1.78 GeV, they are clearly negligible at 1.7 GeV. Then I don't understand any statements that you have been doing for the last 10 years, because now you are making the opposite statement.
No,
of course, I know which one of the two statements is correct.
No, there is not no opposite statement. I mean, I was presenting the talk about the plus and minus, and everything that I said is true. I mean, just look at the plot that I showed at the end.
No,
so there's nothing wrong with the fact that you have more duality violations at lower energies and less above. This is a quantitative fact.
1.77 is not smaller than 1.78.
Okay, we continue this later if time permitting. Now we really have to move on to the next talk.
Okay, first of all, I would like to thank the organizers for putting this all together in what's probably the maximally difficult format. It is both hybrid and in person, so I appreciate that very much. So I would like to talk about the use of the operator product expansion in finite energy sum rules. And I think this might actually somewhat answer the last point that was brought up in the discussion about Diogo's talk. We'll see. So this is working with Diogo and Kim and Santi, and so it's reported in these two papers. And one thing that I cannot refrain from saying is that I'm a little bit surprised that these papers have been out for 3 to 5 years, that these papers have not been answered by the people who favor the approach that I will be discussing here. All right, so introductory slide. Strong coupling determinations. If you read at the FLAC review, and I like to read it because I'm part of FLAC, it says that you basically should stay away from this whole region, right? But of course, if you are interested in the strong coupling from tau decays, you have no such luxury because the tau has the mass that it has, and of course, if you would throw it out, then you lose a potential opportunity for a very high precision determination. Of course, this is if non-perturbative effects can be controlled, which is what all the discussions are about. And of course, it's also a nice direct test of QCD running based on experimental data. Okay. So clearly, we need to face the need to control non-perturbative effects. That is basically what all the discussions are about. And they are usually talked about as the operator product expansion and for hadron duality violations. And I don't have to explain anymore what those are because they've been explained in the last 4 talks. And so it's very important to test your assumptions. Okay. And it's particularly important because, as you can see, the values that are being reported in the literature range over this wide range at the Z mass. So there's a clear disagreement, right? And since these are largely from the same data sets, this disagreement is much larger than these numbers are very correlated. So this disagreement is much larger than those errors that are shown there would seem to imply. All right, so this slide I almost can skip because this is the same thing again. We use let me actually directly go to the next version of the slide because this sets up some notation I can use later. So we use finite energy sum rules. On the left-hand side, you have some linear combination of, I should use the cursor here. I have some linear combination of polynomials that I make into weights, as has been discussed by all the previous speakers. And so then rho s is the spectral function measured in tau decays. So that's or in E plus E minus. And so that's the experimental information. So I'll refer to the left-hand side as the experimental input, and then on the right-hand side we have this theory representation, which is represented by this integral over the circle at radius S0. And so this theory representation has a perturbative part, which is basically the d equals 0 term in the OPE, which is where we extract alpha S from, and which has been calculated by Bykov and company to 4th order in alpha S. Then there's the OPE, the higher order terms in the OPE, that's the higher order condensates, and then duality violations. Okay, and as Santi already stressed in his talk, the OPE is not a convergent expansion. It's at best an asymptotic series. Okay, and so that means that these coefficients C4, C6, C8, and so on can be expected generally to grow in size. Okay. Another thing that Santi also already pointed out, of course, that because of the residue theorem, if you put in a 1 over z to some power here, the z to the n picks out a particular term in the OPE, right? So the power z to the n in the weight picks out a 1 over q to the 2n plus 1, you know, in the OPE. So finite energy sum rules with polynomial weights can be used to really zoom in on particular terms in the OPE. Okay. And duality violations, I think, have been sufficiently explained already, but I want to make a comment on that. Okay, this shows the non-strain spectral function from hadronic tau decays. This is the Aleph data. It's the V plus A combination that has been advertised by, you know, by groups one should use. And so this is being advertised as looking very flat in this region. And it is, of course, much flatter than V or A separately. Okay, but I would argue that this is not flat, right? Here I show the same slide again. Okay, what I did is I subtracted, you know, I subtracted the one that's what I show here. That's the one that comes from the particle model. So that's just 3 quarks here, right? So the difference between the line at 0 here and this dashed line is what QCD perturbation theory gives you. Okay, so that's the alpha S dynamics of QCD. And the data show this oscillation around it that has an amplitude that is comparable in size to the whole dynamical perturbative effect. Okay, so duality violations in this quantity are not small. Now, whether you decide that at m tau squared you can ignore them or not, I leave up to your decision, right? The data don't give any information on this. Okay, so we think that this tells you that you have to worry about duality violations, and even if a lot of pinching helps you to control them, you should show that you control them and not assume that you control them. Okay. So, as is clear from all the previous talks, there are basically 2 strategies to deal with this non-perturbative contamination that we have to deal with in tau decays. One, I will discuss, you know, the topic of my talk here is what we will call the truncated OPE strategy, for reasons that will become clear in a second. Okay, and the other one is the the strategy that's been used by Santi and Diogo in their talks, which I will not discuss here because it's been, you know, very well discussed by them. Okay, and so I would like to stress that both of them contain model components. We have to do something about non-perturbative effects, and like everybody in this audience knows, you know, non-perturbative effects is something we haven't solved QCD, right? So, but also this truncated OPE approach, which is being used by, you know, most lately by Tony Peak and his student, and by you know, the Aleph collaboration, and previously also by Opal. You know, so first of all, they suppress the dangerous region where duality violations live, which is on this Minkowski axis in that complex plane. Okay. But you know, they suppress them by pinching and then otherwise ignore them. Okay, the pinching is done by using polynomials with multiple zeros at that dangerous points here in the right in that diagram. Okay, and that means you have to use high order polynomials. The polynomials I use go up to degree 7. Okay, and the residue theorem tells you that that picks out OPE coefficients up to dimension 16. Okay. Now, since they also want to work at only one value of S0, which is m tau squared, to be at the highest available energy in tau decays, okay, that means that you just have basically as many data points as you use polynomials. They typically use 5. You can only fit 4 parameters. So that means that you have to set many of these higher order terms in the OPE equal to 0. And this is a model assumption. This is a by hand choice. Okay, that's not based on any insight that we have about the behavior of the OPE in QCD. And what I want to show in this talk is that basically leads to that this very choice is inconsistent, and I can show that using data. All right, so as you know, Tony told in his talk, they have looked at very many classes of weights, and I'm going to only use one example. We have looked at, you know, basically all of the sets of weights that have been used, you know, in the truncated OPE approach, but just for sake of the talk, I'm going to just give one example. So here's a set of so-called optimal weights. So those are the 5 weight functions that are being used in the truncated OPE approach. They all, as you can check, have a double zero at this dangerous point on the Minkowski axis. Okay, and since they go up to degree 7, they get contributions from the OPE to dimension 16. Okay, now C2 is basically 0 if you ignore the up and down quark masses, which is a safe thing to do. These weights do not have a linear term in X, so there's no C4 contribution according to the residue theorem. So what you pick out is contributions to C6 through 16. You're only allowed to have 4 parameters because you have 5 data points. So you pick alpha S and the 3 lowest dimension terms in the OPE that contribute, and you set the other half equal to 0. Okay, and then you argue that, as I said already before, that all of these non-perturbative effects are less severe in V plus A. So that's the case that we will consider in this talk. Right, so here I'm going to compare, as a sort of warm-up, 2 choices. You can choose either the choice that's being made in the standard approach, which is set the higher order coefficients equal to 0, but I can make some other choice, right? Another choice that's equally arbitrary, but reasonable. The numbers grow. Now they grow with the order, but that's, as Santi explained, you expect in the OPE. So this is no, as long as you don't have any outside information on the OPE, this is a choice that is equally defensible. Okay, and then so you set these parameters equal to those numbers. So you still have the same number of free parameters in the fit. So you can do the fit in both cases. Okay, so choice 1 gives you these fits that you can also find. These results you can find in Tony Peak's paper. Choice 2, which has the only change is the values of C12 to C16, gives you these numbers here that are vastly different, right? And note in particular, the huge shift in alpha S, right, that is completely incompatible with the errors. Of course, the OPE coefficients come out larger, okay, but the picture is that it's consistent with the OPE being a expansion. Okay. Now we can do more, okay, because in E plus, of course, in tau decays we're restricted by the tau, but by the value of the tau mass, we cannot peak beyond, okay. But you can use E plus E minus data to test this further, right? And the R ratio data that are now widely available to high accuracy, they're not limited by the tau mass. So we can test this to use this to test the truncated OPE approach, because if the truncated OPE approach works at S0 equals m tau squared, so if your modeling of QCD works at m tau squared, it should certainly work at S0 larger than m tau squared. Nobody will disagree with that. Okay. Of course, if you use E plus E minus data, there are some differences. First of all, as Santi already said, there's no actual photon, so we don't have V plus A. Okay. But I'd like to point out there that the truncated OPE approach finds at least equally good results. So their V only fits lead to results that are completely consistent with V plus A, and actually usually with slightly better chi-squared errors. So there's no reason to dismiss V only analysis. Okay. Of course, also E plus E minus data contain an additional isospin 0 component, but that's related by SU3 flavor symmetry to isospin 1. We're looking at pretty high energies from the point of view of the strange quark mass. So again, we don't think that that's a very severe assumption to make. And as we did in our own work on E plus E minus, we use the R ratio data from K and T. Okay, so I'm going to tell you some exercises with this. I want to mention one point. If I call something a diagonal fit, that means that I'm in the chi-square throwing away correlations, but in the errors, I will always fully propagate any full data covariance matrix. So it's not like we're throwing away data covariances. Okay, so here we first try to do the same thing as before. We use these optimal weights as an example. And again, we did this for all sets of weights that are being used in the truncated OPE approach. So you set S0 equal to m tau squared. So the only thing you change is you change the tau data for the E plus E minus data. You do a chi-squared fit. You find a fit that looks like a reasonable value of alpha S, but the p-value is a complete disaster. So then you think, well, maybe there's an issue with the correlation in the data. You try a diagonal fit, which has a larger error. That's not a surprise because you're not doing a correlated chi-square fit, but the number is completely different.
So doing this at S0 equals n tau squared is a complete disaster. Okay. Then you think, well, okay, now I can allow myself to go up to larger values of S0 because I'm now working, I still have data. Okay, so let me try to increase S0 to see at what point might the truncated OPE approach start to work. Okay, and you find that you get a good p-value at S0 equals 3.6 GeV squared for the optimal weights. For other sets of weights, it's slightly different, 3.6, 3.7. Okay, and you find a good chi-squared fit because I raised S0 enough. You find that the diagonal fit agrees with the chi-squared fit, so this all looks fine. You of course get quite low values for alpha S. I'm not sure that anybody is ready to believe these values, but maybe this is what it is, and maybe truncated OPE approach would start to work at values of S0 well above the tau mass. Okay, so but we can do more than this. Okay. So the question at this point is, maybe does the strategy maybe work at S0 equals 3.6 GeV squared? And so the strategy, the model assumption that's being made, I remind you, is that you basically throw away the higher orders in the OPE that the theory tells you you should keep. So you assume that they're negligibly small. Okay, so now let me do. So I do the fit at a certain value of S0 equals S0 star. So in my previous slide, S0 star was equal to 3.6 GeV squared. Okay. Now, if you do the fit at that S0, there should be a very good match between theory and experiment above S0 equals S0 star, right? Because again, theory gets better at higher energies. Okay. So what we do here is I show here all the 5 weights as a function of S0. So the red points are the data points. They're of course highly correlated because the R ratio data are already correlated, and if I integrate them in these finite energy sum models, they become even more correlated. And the black lines or the blue curves, you can see whether they're blue or black, they show the theory. Okay. And so it looks, and the fits are done at 3.6, right? So this looks maybe not so unreasonable, but then you look a little bit closer and you start worrying that for at least 3 of those weights, the slopes in the data and in the theory are rather different. Okay, and so this is now a tricky thing because there's correlations between everything. The data are very correlated, but the theory and the data are also very correlated. Okay, so what we can do is we can look at this in a better way, right? So at this point, from those plots, it was very difficult to judge, whether theory and experiment are in good agreement above, S0 equals S0. What we can do is we can look at what we call double differences. So we look at the correlated difference between theory, the theory side, once you have done the fit, right? So this is fixed by the fit minus the experimental data, taking all correlations into account, including the correlations between the data and the parameters that you fit from the data, so they're strongly correlated, okay? And you do that relative to the point where you did the fit, right? So this double difference, by construction, when you go to S0 equals S0 star, is going to be equal to 0, okay? Because that's where you did the fit. You declare that the fit was correct and fine, and you only look at the consistency in the functional behavior as a function of S0 above the point where you did the fit. Okay, so this double difference should be consistent with 0 if the truncated OPE approach is to be valid. Okay, so you can do the work, and these are those same 5 moments again for the optimal weights. Okay, and you see that. So the point in the middle, right? There's always a point in the middle where there's a 0. That's the point where you did the fit. So that is why these double differences by construction are equal to 0 with 0 error. And that's what you see in these plots. Okay. And then these arrow bars take all correlations into account, the data correlations and the correlations between data and theory. Okay. And that's how you should compare theory and data. Okay. If you want to check whether a fit is good. And you see that these fits are basically a disaster. Right, especially in the 3 weights where I was starting to get worried about the slopes, you see that there's no way that these points are in agreement with the 0 within these errors. Okay, so to us this shows, based on E plus E minus data, that the truncated OPE approach just fails, even at values of S0 well above the tau mass. And that already brings me to my conclusions. Okay, so any approach to dealing with non-perturbative effects and hadronic tau decays needs model assumptions, because we don't have a solution of QCD beyond perturbation theory. Okay, and so in this talk, I considered this what we call the truncated OPE strategy, which is the strategy that was explained first today by Tony. In a model, it's a model in which higher order terms in the OPE are neglected. Okay, so let me also actually make a comment here, right? So it may be, as I showed when I showed these data for P plus A, and I showed how they oscillate around perturbation theory, it may or may not be that duality violations are nicely zero at n tau squared or not. We're not saying that we know that duality violations are large at S naught equals n tau squared, but in the truncated OPE approach, where you do enough pinching that you assume that you can ignore duality violations, you need to make this other very strong model assumption, which is basically the assumption that the OPE is convergent and that you can set higher orders equal to zero. Okay? And so the question then is this dangerous given the asymptotic nature of the OPE? And my talk, I think, basically shows that the answer is an unequivocal yes. Okay. So if you want to obtain alpha S with a competitive accuracy, okay, the truncated OPE approach should simply not be used. It just fails. And that's basically, where I conclude my talk.
Okay, thank you very much. Wonderful. Okay, a question by Tony.
Okay. Maarten, I don't want to get upset, so I will not comment on your slide 14. Anybody can look to the figures, can count how many zeros there are in the vertical scales to see that it's a zoomed scale, and can ask the question, why uncertainties are so small, and in particular because these uncertainties are parametric, while non-parametric uncertainties are not there. So instead of that, let me be more constructive, and let's go to slide 8, please.
But this is what.
Can you go to slide 8?
Sure.
Okay. Here you talk about choices or models. This is a very misleading language. In any perturbative expansion, even the one of G minus 2 in QED, one can put a higher order correction, which is huge. They are asymptotic expansions. And therefore, since the higher order correction is huge, it will change the value we are fitting. But of course, that's not what people do. What people do is try to estimate as well as possible the systematic uncertainty associated with the thing we are computing. And that's what we did. That's what everybody tries to do. Now you put in this table what you call two choices. One are the results of the Wilson coefficient coming from our fit, or an equivalent fit. The other one are two choices that you put by hand for C12, C14, C16, which are huge. They distort completely the fit because you are assuming a complete breakdown of the OPE. And then, of course, your fitted parameters are different.
I'm not assuming a breakdown of the OPE.
You
I'm making an assumption of the OPE that's consistent with what we know about the OPE, which is that it is an asymptotic expansion. So I'm not claiming that these values of C12, C14, and C16 are right. Okay, this is another choice, but it's not an unreasonable choice.
No, I understand.
And what I show is the sensitivity of the result for alpha S to the choices that you make in the OPE. That's all that's going on here.
Let me just finish the argument. I say that I wanted to be constructive. Okay, those parameters are huge, and therefore your fit gives what it gives. In my opinion, they don't make much sense. They don't make any sense. But let's assume for a moment that you are right, and those are the parameters. If those are the parameters, then your assumption that you can neglect the alpha S corrections to the Wilson coefficient cannot be applied, because alpha S correction should be at 20% of the coefficient, and a 20% of C6, for instance, is much larger than the 6.6 one gets from experiment. That means that you need to include alpha S corrections in the Wilson coefficients because they are huge. And therefore, your fantastic and marvelous no weight sum rule, that means not putting any weight in the integral, does not work anymore because all terms in the operator product function contribute to your basic integral. They distort completely the result, and therefore you cannot know what is going to happen there. Therefore, don't play with crazy numbers, because if you play with crazy numbers, this has consequences, and the consequences are not good.
Well, let me point out that these numbers are not the numbers of our own fits, right? For one thing, you know, the C6 and the C8 that we get in our own fits have much larger errors. So 20% changes in those numbers in our own fits would not change the result for alpha S very much. Okay, so this is doing your type of fit, you know, on these values of C12, C14, and C16 that we stuck in as another model for the higher orders in the OPE. Okay, but it's not fair to use this particular table that is that's just an example of what can happen in a truncated OPE approach, you know, to criticize our work. Then you should look at our tables first.
I'm just saying that if you take these numbers, your analysis is no longer valid, because the sum rule with the no weight option that you have taken receives corrections from all terms of the operator product expansion. And these corrections, according to your numbers, are huge.
Also, first of all, as I'm repeating, you know, our own errors on these condensates allow for quite a bit of fluctuation. Second, those corrections, so you should also look at what, I don't remember them by heart, but what the numbers are for C6 and C8 and C10 in our own fits. Also, I'd like to point out that those corrections are not so huge because they're all order alpha S squared suppressed, right? Because alpha S at one loop doesn't run.
Okay, I suggest that we move now to the next talker. Go ahead.
Okay, so let me thank the organizers first for being allowed to give this presentation. So we have been actually, so let me briefly explain the context and what I'm about to do. So we know now how hadronic tau spectral function moments are related importance for alpha S measurements. There's lots of data, and we know that we can get it from theoretical predictions by basically using the vacuum polarization function and including all this analytic calculus to have a nice theoretical formulation. On the theory side, you typically can write down the spectral function moments based on basically there's a tree-level term, then there are electroweak factors. I've actually neglected the electroweak corrections in this formula, but of course they may be included. Then there is a perturbative series that you can gain from the Adler function, which you can derive from the vacuum polarization function in perturbation theory. There are OPE corrections we heard a lot about, and duality violation corrections. The duality violation corrections, they, for my talk, don't play any role. So what I do is not comparison to data, but I'm actually using only conceptual considerations in my talk. Just as a reminder, so what you do is you are calculating the perturbative part by this contour integral, integrating over the Adler function. There are different ways of perturbative prescription, how to do this. I just come to that in a moment. And in the standard way to treat the OPE corrections, you basically have these power corrections, which are inverse powers of 1 over S. S is the squared momentum transfer that enters the vacuum polarization function. Then there are condensates and Wilson coefficients. And then you have all these series, and you can put them into these contour integrals as well. And you can actually see, this is an important aspect of this talk, that for some of these power corrections due to the residue theorem, sometimes, depending on the choice of the weight function, which is typically a polynomial, some of these power corrections get strongly suppressed. You can never get them exactly 0 because of the high order corrections. But if the tree level contribution gets suppressed, because the residue gives you 0 at this point, you typically call that this moment is not sensitive to a particular power correction. So this is an important thing. Now, there are two prescriptions how to determine these spectral function moments. The two prescriptions actually start at the level of the Adler function itself. So you can either expand it in alpha S at minus S. So it means that all the complex valuedness of the Adler function in the complex plane is hiding in the strong coupling. and this constant coefficients here are just constant. These constants here are the coefficients of the Euclidean Adler function, where S is where is just a negative number, real number. And the other way of doing the expansion is expanding in a real scale. Typically, it's the modulus of S, and then you get logarithms of minus S divided by S0, which you can also do by integration. So we all know that we know the first 4 coefficients exactly, and then there is a fifth estimate. There are estimates for the 5th coefficient, which I actually include in all my plots. So you have these 2 prescriptions. I have just written these calculations down. And the problem I want to discuss is that you can see in this picture that what you see here are the moment for the kinematic moment. This is what enters the measurement, the calculations and predictions for R tau. That these bands are the error bands from scale variation, which is between 1/2 m tau and 2 times m tau. This is the usual thing. And we see that FOPT gives large uncertainties, but is systematically higher, and CIPT is systematically lower, right? And of course, what we are interested in here is whether this is systematic or accidental. I will actually not give a clear answer to whether it's systematic or accidental, but I hope that I can convince you that there's interesting new information about that helps to judge it maybe. So there have been some radical statements that CIPT is inconsistent, and I want to give you the arguments for why I think this is true. Whether it's practically relevant, this is a different thing, because this is still a discussion one has to do. But on the conceptual side, I see clear evidence that CIPT has principal problems. And the background is that when you make analysis in Borel calculus, you can see that there is some issue, and you can also see from the behavior itself that there is something problematic in it. So the radical statement is that the CIPT expansion, as explained it earlier, is not consistent with the standard association of OPE corrections and infrared renormalons. And I try to convince you that this is in principle true. Again, whether it's relevant for the actual QCD series, that's a different question. But in principle, it's there. And the problem can be reconciled by a simple scheme change in the gluon condensate, which is very simple and very minimalistic. I try to explain in the second part of my talk. So let me start with some interesting observations everyone can reproduce. So if you don't believe me, put on your computer, do it yourself, and you can check it actually. So if you consider at this moment with this weight function, which is for the hadronic tau decay, this is the moments for which you can actually show that the gluon condensate contributions are strongly suppressed. You can basically neglect them because they're so small. You can actually, if you look at the series for this moment and look at the discrepancy, you can calculate this discrepancy for different values of S0 in theory. You don't have data, but it doesn't matter. You just do the calculation. It turns out that this separation here scales with the 4th power of the square root of S0. So it's actually proportional to a lambda QCD to the 4 divided by S0. Now the question is this an accident, just that perturbation T happens to be like that, or an indication of a quartic infrared sensitivity? If it is a quartic infrared sensitivity, then this is a clear contradiction to the whole construction, because these moments are not supposed to have that infrared sensitivity. Now, the question I wanted to ask here is it possible that in either one of these expansions, or even maybe in both, some residual lambda QCD to the 4 sensitivity is left, which contradicts the statement that this condensate is 0? This is exactly the kind of the physical background question to what I actually want to address. Now, if you look at the CIPT expansion I mentioned earlier, you can actually see that in contrast to the fixed order expansion, where you have a clear expansion parameter, which is this alpha S here, that there's no clear expansion parameter of the CIPT expansion, because once you've integrated this, then you just have a numerical constant. So there's no real parameter you're expanding in. And I was starting my considerations by actually rethinking about the way how we think about the Borel representation of the CIPT expansion from scratch. So let me briefly explain a little bit how this Borel goes. So once you take the perturbative series for the Adler function, let's start with the Euclidean Adler function, because there everything is unique. It's well known that it's believed, I should say, that the series the coefficients will diverge n factorially at high orders. This is a simplistic view, it's more complicated than that. But the Borel calculus actually does the following. You take that series, let us assume we know these coefficients to all orders, then you make this Borel transform where each power of alpha is replaced by powers of u divided by n factorial. Then the series can actually be summed in a certain area in the complex U plane. And it's also believed that you can basically get information about the full way, how this function looks like by renormaling calculus. I don't have time to explain that. But then you can determine what is called the Borel sum by basically doing the back transformation from this analytically continued function. Then you can get what's called a Borel sum. So this is all well known. And the important thing is that there is a one-to-one correspondence to singular and non-analytic structure in this the Borel function and the OPE terms. This is kind of the paradigms of renormaling calculus. And in the large beta knot approximation, where this Borel function can be exactly calculated, you can exactly see that these poles, these linear poles in 1/2 minus u are in one-to-one correspondence to the gluon condensate. So the large beta knot approximation is a particular approximation to full QCD. I'm not so much dwelling on the actual form of it, but this association of singularities and OPE correction, I think this is well accepted by everyone. Now let's look at the FOPT expansion, and let me explain why the Borel function, which people typically use and called the true Borel representation, is correct for it. So because the reason is because you have a clear expansion parameter, you can deal with that. You have these coefficients in the FOPT expansion. You have these logarithms of this complex valued logarithm I explained earlier. You can actually show in models, but you can actually derive, for example, in the large beta knot approximation, where we can actually have very simple analytic formula, but even in full QCD, it works, that these coefficients are reproduced by taking the Borel function of the Euclidean, and in large beta knot, you just have to multiply this exponentially, right? So you know this function exactly. And because you have the expansion parameter, you use the inverse Borel transform rules, and then you can use this and stick it into the contour integral. So that's all the usual thing. There's nothing new here. The interesting thing is that this exponential here and this exponential here can be combined, and they just recombine to an exponential of the inverse complex valued alpha s, and this is then usually what's typically called the true Borel representation. Now the question is, when you now look from scratch to what CIPT does, is this still true? And the answer is, there's another evidence that actually there's another way to write the Borel representation for that case. So given the fact that this is part of the coefficient because you don't have a clear expansion parameter, in some sense, this is an expansion in the parameter 1, okay? But I can as well introduce the expansion parameter alpha s at s naught, and then divide out this s naught in each of these coefficients. Well, why not, right? And so then you get this expression. And when you do that, you actually see that when you do the Borel representation and do the arguments, that this contribution should be part of the U expansion. And when you do that, you can actually get to this expression here. I had a long paper with where the technicalities and the analytic structures of this integral have been discussed. They are kind of weird. It actually turns out to make mathematical sense out of it, you have to deform this contour in a particular way. So if you're interested in that, I'm happy to discuss this in the backup slides. But the important point is that you can calculate this function, and you can also calculate the difference. And the difference is what we call asymptotic separation. And it really scales like lambda QCD to the d divided by S0 to d half for a given renormalon, infrared renormalon in the Borel function, which we know exists. Okay, so let's check. The first thing is whether this is actually then supported by a numerical analysis. So what I'm now considering here is a very simplified Borel model for the Adler function for the Euclidean. It just has the gluon condensate renormalon. This is not realistic, but as a mathematical question to study the difference between CIPT and FOPT is perfectly valid. And this corresponds in one-to-one to only have one non-perturbative corrections, which is the gluon condensate. And I'm using a very simple moment. Let's not talk about the physical aspects and usefulness of it. It's just one, okay? So I'm not interested in direct relation. I'm just interested in to see what CIPT and FOPT does. So in this, for moments of this kind, the gluon condensate does vanish because of the argument I told you earlier. And That means that if the standard association of renormalons and OPE is correct, that would mean that perturbation theory should be convergent for such a moment. And you can see this is the result. You can see the red dots. These are FOPT. They're kind of oscillating, but they converge. You can prove to all orders that this is really a convergent series. It's not just she seems to be so. You can prove it. But if you now use CIPT, you find it has an asymptotic plateau. So the correction at some point gets smaller and smaller, and then the series diverges. And it also has this gap, which is actually precisely what we're after. So actually already the fact that CIPT does not converge for this moment means that it cannot be compatible with standard OPE. So even the asymptotic separation and all these arguments I did earlier don't matter. Already that means it's a clear contradiction. And that also tells us, because this new Borel representation of CIPT is really, this is the gray line, really describes this asymptotic plateau consistently. It means that this Borel representation I explained here is not a good one. I mean, it has bad physical properties, but it describes the discrepancy very well. You can check it for many other moments. It always does the good job in describing, and it also has the right power behavior. So you can always find that it really is a nice, excellent description. I also want to add that you can see in this moment that CIPT is above FOPT. So in fact, what you can now predict is precisely how this separation and this discrepancy works. And there are actually moments where CIPT is actually not above, but below the CIPT is also above FOPT. So you can construct these moments without problem, because we have now from complete analytic control over this separation. And you can also construct moments where this separation vanishes, and you can see that that's really true in perturbation theory. So this is very reliable. But we want to go beyond this, and now this is about part 2. And what we do now further confirms the statements about CIPT. So what is asymptotic separation? From this, you can do the following important conclusion. The part I did not mention is, actually I mentioned it, but I didn't emphasize it, is that if there is a renormalon singularity in this function, this is the Adler function, so the Borel function of the Euclidean Adler function, then you have this asymptotic separation. If this function did not have any infrared renormalon singularities, then the asymptotic separation is 0. So the important conclusion you can draw is that if for some way you can subtract the infrared renormalons out of perturbation theory, then the asymptotic separation should be gone. And if the gluon condensate is the dominant source of that, then we couldn't be able to reconcile the whole theory by just having some new scheme where the infrared renormalons are subtracted. In fact, we know how to do this from heavy quark physics. We know that the pole mass has a renormalon. We know by just switching the pole mass and the scheme to the MS bar mass or to other short distance masses, you can reconcile the problems. It's well accepted. You cannot prove that to all orders that is actually really true, but it's now believed that switching the schemes really systematically improves. It is not just accidental. And in this case, FOPT and CIPT should become consistent. This is precisely what we're trying in this new work. You can easily define a short distance scheme for the gluon condensate. So the typical gluon condensate in our usual calculation, this is kind of like what the pole mass is. It has a lambda pure lambda QC to the 4 renormalon. This is something, this is also well accepted. And now what you do is you're introducing a renormalon-free condensate, which is of course cutoff dependent, and then you are adding to it or subtracting it the series, which is precisely the renormalon divergence which this original renormalon has. And because we know precisely the structure of the Borel representation for that renormalon, I can write this expression down. It depends on the 4th power of some infrared subtraction scale. It depends on alpha S at R, but it has a norm I don't know yet. And this is an important point I want to dwell on later. So what you take is the series. It's well known that the subtraction works for any scale of R, but the important thing is, so because it's like an infrared factorization scale, but the important thing is that you have to re-expand this coupling precisely in the same way as you deal with the perturbative part, such that the renormalon cancels. So this is extremely important. I also want to mention that this simple form is only true in the C scheme, which was introduced by Diogo, Matthias Yamin, and the collaborators recently. In the general MS bar scheme, there are more terms to write down, but this is all equivalent. Now, in principle, now you could go on. And the question is, of course, now we have an R-dependent gluon condensate, but which R should you pick? You can pick any reference scale R if you want. If someone picks another reference scale R, you can calculate the difference and you can show that the renormalon cancels between this prescription. This is the same thing like there is no renormalon, at least no lambda QCD renormalon in the difference between short distance masses. You can interestingly also prove that the derivative of the gluon condensate, this R-dependent renormalon-free one with respect to R is a convergent function. This is a very interesting thing. You can calculate it exactly. You can see all of this in the paper that comes out next week. Now, what we decided is that having an R-dependent renormalon is kind of, let's say, not practical, or let's say inconvenient. So what can you do is to define a scale invariant gluon condensate. Now, actually, you can do that because I know precisely the R dependence of this function. I can actually add a function and define a scale invariant renormalon-free gluon condensate by adding a function to it, which has precisely the same R derivative as this function. You can write it down, it's exact, so I can just integrate it. This function can actually be easily found and can actually show that it happens to be the same as the Borel sum, the true Borel sum of this infrared renormalon, which is precisely this expression. You can write it down here, but that's not important. The important point is that this function can be devised and you can get it very easily. Okay, so in this way, this renormalon-free gluon condensate defined that way now is scale invariant. This is more like what we would like to have. So it's a scale invariant gluon condensate. Just use it. Now, the important point is that this function here, the fact that it's related to a Borel sum is actually not the point. The point is that we can write it down, and the way we treat it is usually part of the OPE. But since I know it exactly up to this norm uncertainty here, I will treat it like a tree-level term. So it's always there. So even if I don't add OPE corrections, I will include it because it just eats up and compensates for the scheme dependence of my intrinsic renormalon-free gluon condensate. And now what you do usually, you get now a modified perturbative expansion by working in these corrections, these perturbative corrections into the perturbative series. And again, you must expand the alpha S in the same way as you do for fixed and FOPT, for FOPT and CIPT. So it means that in FOPT, you expand this at alpha S at S naught, and in CIPT, you have to do this with the complex valued Q square. Of course, then you get logs of Q square and R square. And what you get looks like this. These are the red and the gray line are precisely what we have seen earlier. But once you do that, now for CI, actually it turns out that here in this simple model, because the gluon condensate vanishes, if you use FOPT, all the subtraction vanishes to any order because it's just real valued. And if you stick it into the contour integral, it vanishes in the same way as the gluon condensate vanishes. But if you re-expand this expression in complex Q square and then integrate in the contour, something dramatically happens. It's not zero. The effect shifts the CIPT back to FOPT. And that clearly tells you, it confirms that there's something intrinsically wrong with CIPT. Well, how can a perturbative shift in the gluon condensate by a real valued perturbative series, which would then re-expand, of course, in the complex value Q square with logs, after integral becomes something finite, and furthermore reduces, turns the original CIPT that had the deviation, its divergent, makes it to be convergent and agree perfectly well with FOPT. So that means that this renormalon subtracted CIPT is perfectly compatible with standard OPE. Its Borel sum, because the infrared renormalon is gone, is exactly identical to the FOPT, because that's the origin of the discrepancy. And you see that even CIPT converges way faster than FOPT, which is actually a good thing about CIPT. And that's the reason why I don't want to drop it, but I think that it should be applied in a different way. Now we can go and apply this further. So what I show you now is, let's do this in a more realistic context. So there's been a renormalon model this is a model for the, I used the model for the Borel function of the Adler function, which is way more sophisticated than this one. And it has been called realistic by Benecke and Yamin in 2008. It has UV renormalons inside. It has the gluon condensate and also dimension 6 renormalon contributions in it. And you can apply it with the same polynomial, which is relevant for ATA. Okay, and these pictures are a little bit more realistic. So we have at a scale variation, and I also want to map that this model predicts that the norm of the renormalon, this is the norm of this term in the Borel function, is around 4.5. Okay, and these are the plots you get from the original CIPT and FOPT expansion. This is with our subtraction for r equal 0.8 times m tau. And again, the FOPT, which is the red, is almost the same between left and right. It's not exactly the same because the gluon condensate has an order alpha S correction in the Wilson coefficients. They are not exactly the same, but they're almost the same. But again, you see that the original CIPT, which has this huge deviation, now becomes perfectly fine and compatible with the FOPT case, because the renormalon is basically subtracted prior to doing the contour integration. I also want to mention is that this may be a little bit misleading, this picture. The coefficients up to the red line are known. This is what's typically entered in actual phenomenological analysis. Everything beyond is, of course, model dependent in the sense. But you can already see at the available 4th and 5th order that this situation gets completely different than before. You get nice agreement between the two predictions. But we can also go on. So if this is true, let's look at models at moments which have typically not been considered recently, where the gluon condensate is not suppressed. So this is, for example, 1 minus x cubed has a term in it such that the gluon condensate is not suppressed and gives you a huge contribution. Now, that also means that the renormalon is not suppressed and should be visible. This is what you find in the usual FOPT and CIPT. The series have huge uncertainties, and there's no sign of convergence because the renormalon has this linear rise and as order, which is the typical thing you expect from renormalons, that this linear rise here, the true answer should be somewhere here where it kind of looks linear, but you have huge uncertainties and from it. Now, because we have subtracted the gluon condensate, things should behave much better, and this is what you get. It's even like this happens to be like unnaturally small scale uncertainties. The fact why CIPT has very small scale uncertainty seems unnatural, but it happens because of the interplay, because of the logarithmic contributions and the real contributions. I think this is, you shouldn't take the scale variation here very seriously. But the FOPT converges very fast, and it actually is totally flat. And you can also see that already at available orders which are used for phenomenology, the discrepancy is very small. And the difference between it is way smaller than the scale uncertainty of the original moments, which means it is now accessible in principle for phenomenological analysis, which people didn't use to have. But of course, I need to add that that this picture has been done with this model, and therefore, of course, is an uncertainty on this norm, and that's something one has to address. So anyway, I'm done with my talk. Let me just summarize. So I made the radical statement that if the CIPT, the original CIPT, is not consistent with the standard OPE approach. I come to this also later, what it really means. What my statement is that in the presence of infrared renormalons, that this is a mathematical statement, and I think I'm happy to defend it heavily. And the difference, if there are infrared renormalons, I can calculate the difference, which is the asymptotic separation. The separation, the discrepancy between CIPT and FOPT, if you just use it in the usual way. The problems of CIPT can be resolved if you are subtracting the gluon condensate renormalon. So everything we observe here seems to be consistent with the fact that this norm is maybe even really close to 4.5. With some uncertainty, of course, but everything that we can observe is kind of telling us that this is true, if all, because these mathematical contributions I calculated are true. And we have devised such a scheme, which is very minimalistic. It's very transparent, and there's not related to very complicated analytic analysis. but it depends on an uncertain, on a new parameter, which is the norm of the gluon condensate. So for the pole mass, this is actually can be determined very precisely to even a few percent. For the gluon condensate, it's unlikely that you get ever to this precision because the more further away a renormalan is from the origin, we know that, then the determination quantification is always more tricky. But I also want to mention is that for the pole mass renormalan, it's actually is known that the gluon, the lambda QCD renormalan really dominates the series, which it gives you like 95% or almost 100% of the corrections at 4 loops. Our improvement here does not rely on that. I mean, it turns out that with this norm, the gluon condensate contribution are not the major part of the 4 and 5 loop corrections. But they are significant parts, so like 25%, 30% is sufficient that this is really working. So it's not really a very restrictive assumption. And I think you can determine this norm. But of course, there is some assumption in the background that everything we observe here is not accidental, which is in principle possible. It could be all completely unrelated to renormalans and just the series happens to be like this. So this is the basic question one has to decide on. But I'm happy to make that assumption because everything I see from all the observations, all these moments here, these are I picked 2, but you can take any moment. It's always the same observation. It seems that it is really true. And so if you use this new scheme, the disparity between CIPT and FOPT is reconciled. And that means, of course, that these moments, which people have not used before, now are accessible to determinations of the strong coupling. Even the gluon condensate can be determined very precisely from it. We'll show that in a future paper. And the classic moments, which only are relevant for alpha S determinations, and if you apply this method, then the discrepancy is reduced. Okay. So let me just summarize the basic points at the end. So the known 4 and 5 loop corrections are fully consistent with the assumption that the sizable gluon condensate norm exists with around 4 or 4.5. It's still possible that discrepancy is completely accidental and that perturbation it just has this norm and beyond 5 loops, things behave completely different. That's not excluded, but that can only happen if the norm of the gluon condensate is very strongly suppressed. I don't want to be that. This is a very unnatural assumption, I believe. It's not excluded. It's all accidental and just looks like this. But this is the relation. So if you believe that, then it means that the norm is 0. And this is kind of unnatural, at least from my perspective, but in principle possible. And all studies actually support the CIPT, FOPT discrepancies of infrared origin. Anyway, I believe that this opens up new doors. And that means that new high precision determinations can be done. Also using CIPT, because I believe it sometimes really converges way better with the usual arguments which Tony made, but not the original one. Okay, thank you very much.
Okay, thank you, Andre. I see a question by Tony.
Hi, thanks for this very instructive talk. I mean, I'm not sure I can agree with some of the interpretation, but certainly you have given a lot of very useful information. So I think it's going to be very useful. I have a question I think I already asked you some time ago, and I would like to know whether you did progress on that. Can you put your first backup slide?
Yes.
Okay, here, because here you have a figure that is very transparent. I think you agree with me that perturbation theory at any given finite order in perturbation theory has no problems of analyticity whatsoever.
Yes.
It doesn't matter whether I use fixed order or if I use contrary proof. So we are talking about the resummation.
Yes.
What bothers me is the fact that there is a Borel ambiguity in what you call fixed order perturbation theory, while it does not seem to be any Borel ambiguity in what you call counter-improved perturbation theory.
Yes.
And put in a different way. In this figure in the right, you show that the 2 Borel transforms give exactly the same result for a given choice of the Borel ambiguity of fixed order perturbation theory. Of course, this is not the right choice because then you have analyticity problems.
Yeah, I can ask you a question very easily.
Okay.
So the fact that at each order in a perturbative expansion, you don't find a singularity or a cut of any of this kind, but you have it in the complete function. I can give you example for it. Take about how do you actually represent the delta function or the integral of it. We know that the finite representation of distributions is related to functions which have no delta functions and no cut. They're all smooth and well behaved. And it comes from a certain prescription of resummation that you define a cut or a delta function. So this is a quick answer. What this Borel representation does, of course, it tries to quantify the, let's say, kind of the true resummed value, and it has a cut, which the original functions do not seem to have, but the perturbative behavior builds up this contribution. But at any finite order, you can see it. There are actually way more stuff I would like to explain to you here in this picture. I'm also interested in knowing what the objections about my interpretations are, which you didn't ask. But maybe this is in the discussion. Anyway, but this is the quick answer to your question.
Okay, no, but my question is still there. Why in your contouring proof perturbation theory Borel, or what you call like that, why there is no ambiguity whatsoever?
Yeah, and the reason for that is that this Borel representation doesn't follow the usual rules of what we would usually assume to be true for the Borel calculus. This is totally sick in it characterizes the property of CIPT, and its sickness. What you're asking means for me that's the proper quantification of the problem CIPT has. Now, everything you're saying is a statement about CIPT and not about this representation. This is because you can derive this expression by assuming that the complex valued alpha S powers are part of the coefficient. If they are part of the coefficient and not the expansion parameter, that this expression is this conclusion that this is the right representation is it's enforced. What I also want to mention is that CIPT is not in the usual context of asymptotic expansion because it doesn't have a clear expansion parameter. So even writing down this expression is already pushing boundaries in some sense, right? Because the question is, in what expansion parameter are you expanding the CIPT expansion? There's no, you get a bunch of numerical coefficients. There's no clear expansion parameter, right? And the reason why this behaves so weird and it looks so weird is because I try to put it into the usual Renormalon calculus language. Maybe this attempt is even wrong. But the outcome is that expression nicely reproduces what CIPT does. And in fact, for all cases, you can try at any moment. And the separation is, you can always reproduce it. I also want to mention something that the region where you see this clear separation between these two series, the gray one and the blue, where here you can really quantify it, that's strongly moment dependent. For other moments, this region where you see this thing really being separated by a gap depends on the moment where in which order it happens. And it can happen that if you have certain combinations of polynomials that the calculated asymptotic separation doesn't seem to agree with what CIPT does. Okay, so this can happen, but we have explained this in detail in our paper.
I have read your paper very carefully, so I understand all that, but my question is still there. I mean, when I see your two equations here.
But Tony, I answered your question very clearly. It's clear that this expression here, because the Renormalon poles are not on the real axis, they are lying somewhere in the complex plane. This doesn't contradict, it just means that the series is not convergent. Of course, if I integrate along the real axis, I cannot define, let me just explain you the others. So what Tony means is that if you have a pole on the real axis on this function or a cut, that integrating along the real axis gives you an ambiguity, and people typically learned that you can quantify it by deviating from the complex plane a little bit and taking the imaginary part as an ambiguity in something that's completely ad hoc. And I think you know that it's completely ad hoc. The fact that this expression is finite and doesn't have an ambiguity if you integrate along the real axis doesn't mean anything, because this function, the CIPT, is anyway not in the realm of standard asymptotic expansions. Take and that answers your question. Of course, I can define a way to modify this, that then I do get deviations, and it's possible by modifying the contour here, and you get deviations. But that's not the point. The point is that you get this discrepancy, and this is the point, that because if this is infrared sensitive, then you find a discrepancy between the both. That's the main point. I was never dwelling in my paper on really estimating and judging the way how to quantify the ambiguity of these two expressions. I just took this and I took this. And I tell you, if you play around with the contour deformation a little bit, then you can find an uncertainty on this. But it won't change the picture, right? So it's a completely secondary question, and it's not to the point. Right, it's not related to the question I'm asking.
Maybe we can discuss later because it's getting too technical.
Yes, indeed. So, Andre, thank you very much again for your presentation. And we should postpone some questions regarding the jets. However, I believe that this is not very controversial, and I would in fact skip now this discussion. What we also have not done is we have not given the possibility to people to ask questions to the presentation of Tony. So maybe this is what we should do now. I don't know if there are questions to this presentation, however.
I have questions.
Okay, so then maybe Tony, you could share your slides, and this is what we can do in the maybe next 10 minutes or so. But Tony? Wow. Okay, if Tony's gone, then thank you. Okay, Andre, would you like to start with the question?
Yeah. So I have a question to page 12.
Yes.
So are you here, Tony?
Tony, are you there? Yeah, I think so. Yes, yes.
Okay.
But we cannot hear him. Not okay.
Okay. So I was wondering, Tony, you argued about the fact that there's certain OPE corrections that seem to be not important. Why didn't you just include them in analysis, and that would resolve the issue? Tony, why do you have to argue indirectly that they're not important? But why didn't you just include?
Tony, you're muted in case you want.
Okay, and you're asking about this. Okay, yeah. Is correct. Okay, at the end is the question of how many parameters do you have and how correlated the data is. So you need to balance the two sources of information. So if you add too many parameters, you finish having fine-tuned fits, which don't give you too much. You can get very happy because you can get excellent fits with very, very precise parameters, but you need to assess what are the systematic uncertainties of your fit. So if you want to think about this in a different way, the moments with lower powers of X are the ones that really fix alpha S. And these moments, they have a small uncertainty, which is given by the rest of moments. So if I go here, for instance, you have these 5 moments that one is choosing. Alpha S is fixed by the first or second moment. And it has an uncertainty which depends on the condensates that you are putting in the game. So the next condensate is the one that gives you information on this condensate. And the next moment is the one that gives information on the next condensate. So at the end, the condensates that you are neglecting, for instance, here I am neglecting 10. So the fact that I am neglecting 10 introduces a huge uncertainty on 8. But it does not introduce a large uncertainty in alpha S. So what we do is we do a second fit, including 10. I think I have this fit.
Did you fit 10, or what do you mean by include? You included?
Well, you include 10 in the fit but then of course it's a fit that has no free parameters. So you are not talking really about a chi-square distribution and things like that. But what you can do is to see how including this parameter affects all the other things that you are fitting. So you can estimate systematic uncertainties, not parametric ones. So what you realize immediately is that this generates large uncertainties in your power corrections, but not in alpha S. In fact, the difference between this exercise and the original fit is fully included as an uncertainty of the final value of alpha S.
Yeah, I mean, Tony, what I'm worried about here is that you're overestimating your uncertainties.
That could be.
Yeah, you're overestimating because you are forcing yourself into observables which you cannot fully describe theoretically. And that's the conclusion I draw from it.
Right. I fully agree with you, but we wanted to be conservative, okay, and be conservative in all possible methods. So when we show, I think, this table means that in each method, we have tried to be as conservative as possible, trying to push all possible problems in the different parameters and see what happens.
No, but suppose
all methods that we have tried, since they had larger problems when changing the inputs, we didn't include in this table, and we didn't include in the determination of alpha S.
Now the actual question I have is, I need to ask that question, Julia.
Okay.
Suppose I take moments which are not sensitive to dimension 10 and beyond, and I get small uncertainties. Would you claim that this is an underestimate because your analysis?
Sorry, say it again.
So suppose I'm making my analysis entirely with moments where all OPE terms are included that need to be included, and I get smaller uncertainties from that reason. Would you conclude from that I have underestimated my errors due to your analysis?
Let's say you don't have enough experimental information to fit so many coefficients. So for instance,
I will not do that. Suppose I take moments where I don't need to neglect any higher order terms from the OPE. And but I get smaller uncertainties from that.
You mean you take moments that only depend on one or two coefficients?
Yeah, suppose I take moments where I don't need dimension 10, where dimension 8 is sufficient.
Yes, you can do that.
Right? And if I get smaller uncertainties from these moments, would you say that I underestimated the errors if they are smaller than yours?
Well, let's see, you can do the following. In fact, we did. You can take, for instance, this moment, 2, 0, which only depend on two condensates. Okay, and then use the experimental distribution to fix alpha S and the two condensates. But then in order to have enough experimental data, you need to follow the S distribution of the experimental data. So you do that and you get nice results. But then when you analyze the uncertainties of your fit, because you are following the S distribution of the data, you are much more sensitive to things that you don't control so well, because you need to go to lower S values first, and then you have problems. Second, the experimental data points that the different beams are highly correlated.
Yeah. Let me just point this out to you, okay? There is no way out, okay? If you include all the terms in the OPE, you have to lower your S0 below the tau mass, and then you have to include duality violations.
Okay.
There's no way out.
It's an experimental kind of, yeah, I don't have enough data, you say. Okay, I understand.
And all of this whole analysis is based on the assumption that the OPE is convergent, which we know is not true. Right? All these statements about you add one more condensate, you check that affects only the condensate just above it and not alpha S. This is fundamentally dependent on the assumption that the OPE is a convergent expansion, which is simply not true.
Well, it is not true that the OP is convergent, and it is not true that the perturbative expansion is convergent. This we know. Now you need to assess your systematic uncertainties in the best thing that you can. And by the way, let me put these tables, which show what is the size of duality violations at the tau mass scale. Okay. Before, Diego was saying that at 1.8 GeV in energy, duality violations are negligible, while at 1.77 GeV, they are important, and I was complaining. Okay, in this table, you see the size of duality violations for different moments compared with the experimental number, with the experimental uncertainty. For normal weights, so n equal to 0 is what Boito et al. Are doing. And you can see the size at the 1.2 GeV and at the tau mass scale, and the size of this duality violation with pinched waves, the simplest one. And as you can see at the tau mass scale, they are completely negligible. So I don't know what we are discussing.
David, would you like to add something?
Yes, I'd like to maybe ask a very naive question. Is it possible to solve all this? Because I mean, we have been having this discussion since 7-8 years. I mean, some of you have been working on this for 20 years, 30 years. Will we solve all these problems if we had much more precise and accurate experimental data on the tau lepton spectral function, both for the axial and vector? Or this, even assume now we have the ultimate measurement of experimental measurement of the full tau spectral function, all these problems would remain, or they will be solved?
Let's say things will improve a lot. Okay? If you reduce experimental uncertainties, then you can play your games in a much more free way. So
basically, you will kill many approaches. Is that what and then converge?
I don't want to kill approaches. What I want is to estimate systematics in a reliable way.
Diogo, you want to add something?
Yeah, no, I just want to say that in the tables that are on the screen, you see the size of duality violations for pinched moments, which I believe are the moments that are used in these analyses. But this is small, and this is expected to be small. So you could even increase pinching, and you have even smaller duality violations. But then the problem is in the OPE. So you could reduce the duality violations to even smaller numbers if you want, but you would create even more problems with the OPE. So having small duality violations around the tau mass, which does not contradict at all what I said before, does not solve the problem with the OPE. So the problem with the OPE remains.
I'm happy that you say that, because that's not what you were saying a few years ago.
Okay, so I'm wondering if we should stop the discussion here, or
can we at least agree what is a way forward in any way? Or because we have to provide some kind of prospects for the next 10 years, and it would be a little bit disappointing to find ourselves in 10 years from now discussing the same or very similar problems.
But David,
yes,
if I understood Andre correctly, then there's the hope that the discrepancy between FOPT and CIPT will resolve itself, and then we get some new numbers from both of them, which will be much better, and we don't need to add some uncertainty for the difference anymore. And that, I hope, is a prospect for the next year or so.
Thank you, Klaus.
That's true. That's why I found so interesting the talk of Andre.
Okay, Stefan here.
Yeah. So yeah, Klaus has stolen my thunder. I wanted to say the same thing. No, it's I think so. I think in this community and problem, people are looking forward to what Andre and colleagues will be publishing very much, because then one can see sort of with results, and possibly also with phenomenological analysis of tau data with this approach, what really comes out of this, and that could be a big step forward.
But what is the opinion of Santi, Diogo, collaborators on I didn't hear, I think, and Kim?
Sorry. Yeah, just a second.
Yes. So I think on the negative side,
Maarten, yes.
I think the CIPT versus FOPT is not a whole controversy. So I don't think the issue will, Andre's work will make a lot of progress on the CIPT versus FOPT issue, but it's the non-perturbative issues that we have discussed that are controversial. On the positive side, I do think that better data will help, right? Because it makes it possible to test approaches more stringently.
And will existing machines provide this data? Is Bell,
Well,
for example?
so Bell 2 can do something there. I think they have done the 2-pion channel. If they will do both 4-pion channels, so they don't have to do a completely inclusive analysis, right? But if we would have in our newest spectral function, we would have the 2-pi and the 4-pi channels from Bell, we could redo that analysis and have a much more precise vector spectral function than we have now.
Any other machine?
Kim, would you like to add
BESS?
something?
What about BESS, the Chinese machine? Will it
David,
help?
there are many hands. Sorry. I mean, we have to give. I see many hands here. People waiting to talk as well. Kim, would you like to add something?
Okay, so there's a couple of things. One is a question that maybe someone like Bogdan could answer, which is an experimental question. So, for example, we know that Bell already gave a very good unit normalized 2-pi distribution, presumably because of the much higher statistics than the LEP experiments. However, the branching fraction for tau to 2-pi at Bell is not nearly as good as the Aleph one. Now, the question is, would it be possible, for example, to imagine Bell 2-pi data, maybe some putative Bell 4-pi data, Bell 2 4-pi data, with very good unit normalized distributions, and then setting the overall normalization by the H-flav values, which are more dominated by other experiments? Or are there some subtle correlations that would prevent this from giving you a good, fully normalized distribution? Because if there's not some subtle problem, then probably there can be significant improvements in those exclusive mode distributions, and that would help within a given analysis framework, reduce the errors. There's a separate point I want to make, but maybe I should make that point first and ask Bogdan to comment.
Bogdan?
Okay, since you asked me to comment on this, I mean, it's true that Bell and Bell 2, I mean, they have a high potential to measure well the shape of the spectral function, but it's, I mean, for the normalization, they do much less well than something like Aleph, just because of the boost. I mean, it's an experimental reason, it's fundamental, and the normalization will have to come from elsewhere. And in terms of prospective, what one may say in the white paper is that this is one place where FCC-EE will help. I mean, it's really for the normalization of those spectral functions.
But I mean, for example, if one did the following, would there be some subtle correlations that we're missing? If, say, I took the 2-pi unit normalized distribution from Bell and set the overall normalization from the H-flav branching fraction, that would actually be an improvement relative to the Aleph 2-pi distribution because, of course, Bell is much more precise near the kinematic endpoint.
Yes, but
is there some subtle problem, or is that a reasonable thing to do?
No, but I think it has been done already, essentially, because I think the flag averaging is still dominated by Aleph. I mean, for this normalization. And for example, we have looked at this spectral function from Bell normalized with Aleph.
Okay,
sorry, I'm sorry to interrupt. We do have a sharp cutoff here because we have to take a bus. I don't know. I mean, you can also continue the discussion if you want to. Best would be using the MetaMOS channel. Yeah.
It's like recorded at the top.
Yes.
Can I just make one small comment because
yes.
I think this is important. Some of the comparisons that Tony gave in his talk are visually quite misleading. The reason is that, of course, because these finite energy sum rule integrals are integrating over data, just the integration over the same data over different regions of those creates very strong correlations between the spectral integrals for different S0. Similarly, the theory integrals for different S0 are very highly correlated S0 to S0. And in addition, the theory and the experimental integrals are extremely strongly correlated because the theory integrals come after fitting from the experiment. So things that are common in the literature in which you plot the experimental spectral integral with its error band, and then you separately plot the theory integral with its error band and say, look, they overlap. That's completely misleading. That you cannot simply say, oh, the fact that they overlap shows that the agreement is good, because the correlations are so strong that if you push up inside the experimental error band, that will change where the theory band lies. And you have to do these correlated differences that take the correlations between the fit parameters and the experimental data into account. So that's the whole point of the double differences that were shown in Maarten's talk. And all of the uncertainties are plotted in there. So the types of independent theory bands and experimental bands, those plots should just be thrown away. They are completely misleading.
I don't know,
What
Tony,
is
if you want
misleading
to.
is to hide the theoretical uncertainties.
Okay, maybe we continue now the discussion really on the MetaMOS channel, and we'll have to leave. So thank you very much to all the speakers again.